So in the last session, we learned about decision trees, right? So decision trees is like making decisions using the tree structure. So based on the information gain and entropy calculated at each level of the tree, we decide which has to come first as the root node, and what will get appended based on the information gain of different subtrees that we are going to that we have constructed. So that is one type of classification method that we use to classify different data points to a specific class. So today, from starting today, we are going to learn about other classification methods. Like one of such kind is k nearest neighbors. So this is a classification method. So we will encounter many classification methods. Now, most probably we'll complete everything by tomorrow. So what every classification method will try to do is that it will try to classify a given given data point to a specific class. So that is all what it will try to do. So let's suppose if you consider all of these as different data, different classes here. So when you get a new data point, what you all have to do is that assign that particular data point to a specific class. Okay, so this is one kind of class. This is class one, this is class three, and this is class two. We have three different classes here. So what does a classification method? These classification methods will do is that given any point, it that classification method will try to assign a class to that given data point. So here there are three classes. What the classification method goal is that when any new given point is given, whenever when any given point is given, so it will try to assign a class to this point, whether it is class one, class two, or class three. That is all what we train the methods to do. Okay, so it has to predict that particular point efficiently. That's what we do in classification training. So we take a specific approach. We train that model using the data set that we have. We break the data set to training set and testing set. Using the training set, we train the model, and then what we do is that then we take the test data set and test how the model is performing, calculate the accuracy of that model, and if needed, we tune that particular model better to give much better accuracy on the test data, so that once we get the desired accuracy in the training process using the test data set, we then use that data to use that model to predict the class of a particular point on an unknown data set. So this given point is an unknown data set. When we get that unknown data point, the primary goal of this classification methods is to assign a class to that particular method. So this is all what we are going to explore now. What are the different ways that we can train the model, and what is the effective which particular classification method is effective in which case, and all that stuff we are going to study. And we have studied a simple classification model in the last session, which is decision trees, and we constructed an effective or optimal decision tree based on the information gain of a particular of a subtree that we have constructed, right? So that is one example of classification method. So today we are going to study about the other method, which is KNN. This is the simplest. To understand this is very simple. So in K nearest neighbors, what we do is that we calculate the distance of the given point to every other point in the data set. Okay, so if you look at this, so this is the given data point for us. So these are all existing data points that we do have. So what we do is we calculate the distance from this point to every other point in the data set. Okay, it can be n number of points. We are going to calculate the distance of this point to every other point. So when you calculate the distance, what is the formula that you can use? You can use Euclidean distance, or you can use Manhattan distance, and you can also use Mahabhalonius distance. Okay, so we also have studied about why Mahabhalonius distance is more effective than Euclidean distance. I don't want to go there again. So now, if you use Euclidean distance or Manhattan distance is not just nothing but an absolute distance. Whereas Euclidean distance is nothing but square of the distances between yeah, every other point and then do a square root of that. Okay, so we can actually go ahead and do those calculations on a sample data set shortly. But let's understand the concept. What we do is we calculate the distance of this given point to every other point in the data set. Once we calculated all the distances using any of these formulas, what we do is that we then short the distances from that given point to every other point in the data set. So in the data set, we have around 11 data points, right? So here there are 5 data points, and here we have 4, and here we have 3. So 5 plus 4 plus 3, 8. What is 5, 4, 3?
Well,
So we have around 12 data points here, right? So now, what we are going to do is to all these 12 data points, we are going to calculate the distance from this point, and we then sort the distances in an increasing order. So what this says is that the distance from the given point, the distance from the given point to D4 is the shortest distance. That means D4 is very close to this point. That is what it means is. And then after D4, D1 is closer to the given point. So after D4, D1 is the closest point to this given point. Such a way, we calculate the distances from the given point to every other point. Okay, so this is a given point, and these are all, these are different points that are in the data set. Okay, once we calculate the distance from the given point to every other point, we calculate the distances and then do sort the distances in an increasing order. Then how do we classify this given point? The whole goal is to classify the given point to a specific class, right? What we do is we take a k value. Okay, so here the k is given as 7. Let's not bother about how to decide this k value. We will come to there shortly, but let's focus on how to classify based on this k value. Now, if you're given 7, k value as 7, you just have to consider 7 points from the top. Okay, I mean, what it does actually means is that we are trying to consider only 7 points which are closer to the given point. So we are considering only 7 points closer to given point. Okay, closer to given point. So, and then what we are doing is, now let's calculate, out of these 7 points, let's calculate to which classes these points belongs to. Now, if you look at this, 3 points in these 7 points which are closer to the given point belongs to class yellow, right? So these 3 points belongs to class yellow. And now we have 4 points out of these points belongs to this gray color class. Okay, and we have no points belongs to red. Okay, and now once we calculated the accumulation of points belongs to different classes, and then once we have this count, we decide that the given points belongs to this gray class just because the count is more for this particular class. Okay, so that is how KNN actually decides the class of the given point. So to rewind, given any point, calculate the distance of every other point to that given point, and then sort the distances in the ascending order. And then given a k value, I mean, that's a user specified value, and that user has to decide that specific value. So once the k value is given, and then calculate the points, calculate the count of the points belonging to different classes, and choose the point and choose the class whose count is more in that picked points. Okay, so intuitively, to understand this, we are taking the closest points for this given point and then choose the class of the points. I mean, what we are trying to do here, we are trying to assign the class to this particular point based on the majority of the classes that fall within that boundary. Let's suppose if you are taking 7 points here. So let's suppose these are the 7 points closest to this given point based on the distance calculation, right? So these are the 7 points closest to this given point. Now, in these 7 points, more number of classes, more points belongs to class 2, which is gray class, right? So the count of these points is 3 and the count of these points is 4. So it is more, it makes more sense that assigning this point to the class where the points are more likely or more belonging to, right? So in this particular zone where k is equal to 7, that means picking 7 points closer to this given point, the class 2 points have more count. That means majority is class 2. So we assign this point to class 2. Okay. So if in the other case, if we take, let's suppose if you are going to take k is equal to 3. Okay. Now if you are going to take k is equal to 3, what happens? If you're going to take k is equal to 3, we restrict the points to 3. And now here the yellow points are has count 2 and the gray is 1. So now we have to assign that given point to yellow class, which is class 1. Okay. So if you are going to take 4, what happens? 3 and 1. So yellow is 3 and the gray is 1. So we are going to assign the class to yellow. So that is how KNN decides the class of the given point. Okay. Now, you have to understand how to pick up a k value. Now, if you look at k is equal to 7, we are going to assign the given point to class 2, which is gray class, right? If k is equal to 3, the classification result got changed. We are assigning to class, what is that? Class 1, which is yellow class, right? If k is equal to 4, we are again going to assign that to class 1, which is yellow class. If so, as k value is getting changed, the classification result is also changing, right? So it is now the goal is to find out the best k value which is giving high accuracy. So how to choose this k value, which gives us more accurate results in the classification? So the main goal is, given any new data point, we have to predict, we should be able to predict the best class for that given point, or we should be able to accurately assign a class to that given point. So that is whole goal. But we also have seen that as k value is changing, the classification result is also getting changed. So that is impacting the method's accuracy, right? The method's performance is directly proportional to is dependent on the value of k. So it is very important to choose the right k value when you are designing this particular model. And now you will understand how to actually choose the right k value for this KNN method. Okay, so for choosing the right k value, you have to understand a concept called as cross validation. Okay, so using these cross validation techniques, we will most probably tune every parameters of different machine learning models. So k is a parameter that needs to be tuned. Okay, so that is not something you can guess and give to that particular model and expect that to perform well. It is not how it is going to work. You have to tune that value of k so that the accuracy of the model is getting increased. Okay, so the tuning is being basically performed using this cross validation. So what is this cross validation basically means is that cross validation allows us to compare different machine learning methods and understand how well they will work in practice. Okay, so cross validation is just like comparing the results of different machine learning methods and how they will work and understanding how they will work in practice. So we will actually, in short, we will train the models, test the models with different values of k. If you take the kn and pick a value that is where the accuracy is more, it is as simple as that. So given a data set to you, if you're given a data set, using that data set, break that to training and testing, and then rigorously train the model using different k values. Let's suppose if I take k is equal to 3 and train the model, test the model, and calculate the accuracy. Okay, I'm going to calculate the accuracy of that method. And then what I'll do next is again choose a different k value, calculate the accuracy, choose a different k value, calculate the accuracy. Okay, and then you have to come up with the best k value where the accuracy is high. That is how you tune the value of k. Okay, that process is basically cross validation. That is what we do in cross validation. So cross validation allows us to compare different machine learning methods. It's not only different machine learning methods, it also outputs of different tuning parameters of the same method also falls under the same case, and understand how they will work in practice. Okay, so how understanding how they are going to, I mean, comparing the different machine learning methods, and then analyzing how they work in practice is what cross validation actually do. Is let's understand this with an example. So if you're given a data set, let's consider this blue bar given over here is a data set. Okay, so now what you need to do with this data set, you need to train the machine learning model and also test the machine learning model using this data set. So now what you basically do, you break the given data set into training data set and testing data set, right? That is what you do. Okay, so it's not ideal, it's a terrible approach. Like, you cannot use all the you know all the given data set as training data set. It will give you measurable results when you actually test the model on a given data set, because you are giving every insights in the data. You're not keeping the data aside to test your performance. So when you give every data point in your data set to the method, it will get tuned to those values. So whenever you cannot actually predict the accuracy of that particular model. Even when you give all the data set to the model and train to it, it will get tuned to this. It knows all the values of this, right? It knows the outputs of every value in this data set. Now even if you pick a specific set after training the entire model with the whole data set, and even if you pick some data set out of this total data set to train this model, it will always give 100% accuracy, because it knows the outputs of those points. So it's going to perform well. But that's a terrible approach. You cannot anyways, should never train the model with the whole data set that you do have. What you basically do is you split the data, and you will use some part of the data to train the model and the rest of the data to test the model. That is how you calculate the accuracy, because you're not feeding the labels or the outputs of the specific data point when you're training the data set. Okay, right, when you're actually predicting the model using the test data set. So that is how you are actually calculating the accuracy of the model, right? So what in general what we do is, I already explained you like how we split the data set, how do we train the data set, how do we test the data set, and how do we calculate the accuracy. Accuracy is nothing but number of labels that it got correctly predicted by the total predictions, right? So let's suppose if it has, out of 6 data points that you have fed, it has predicted 4 as right and 2 as wrong classes. The accuracy of this is 4 by 6, which is where out of 6 it predicted 4 labels correctly. So that is what accuracy is. So when you're testing these models, these points, you will not actually give the label. So you will keep the label with you, which is the known label of that particular class, and you will get the predicted label from the machine learning model. So we call this as y cap. So this is the predicted one, this is the actual one. So this is model predicted values. This is your known values from the data set that you have got. And then you will compare both of them. So if both got matched, you will mark that as correctly predicted. If both are not matching, then you will call that as not rightly predicted. So this falls under this particular category, this falls under this particular category, right? So now coming back to the cross validation, we are discussing about breaking this given data set into two parts. Okay, so 75% of the data is used to train the model. This is, let's suppose this is model, some model X. Okay, this is basically a logistic regression model, but as we haven't gone through it, let's consider just as a sample model. So to actually train this model, we have used 75% of our data that is given to us, and 25% of the data is used to test this particular model to calculate the accuracy or other measuring parameters. But the question here is that is good. We have used some part of the data in the given data set to train the model, and some part of the data to test the model. But the question now is, how do we know that using the first 75% of the data for training and last 25% of the data for testing is the best way to divide the data or split the data? How do you know this is the best, this is the best split? Why not this split? So why don't we use first 25% of the data as testing and the rest as training? Okay, why not this 50 to 75% of the data as testing and the rest as a training? Okay, how do you know which is the best split? Okay. So what this cross validation do is, so rather than worrying about the splits that we are doing, it will cross validation will consider all of them. Okay, and then summarizes the results. So if this particular split has given a result X, I mean accuracy of somewhere around uh, uh, what I would say. So let's suppose I have. Let me come back. Like this has given a result of X. This has given a result of Y. This has given a result of Z. It will accumulate all of them, and then finally it comes up with something called something to get you the right value. So you'll understand that shortly. But right now, what you have to understand is, you don't really need to bother about the split of the data set. Cross validation will actually considers all the splits and aggregates the results. I mean, summarizes the results and then decides which model is performing better, or which tuning better, or which tuning parameter better fits in particular, which value better fits a tuning parameter. So that is what you will understand that. So as of now, you have understood cross validation is nothing but it will actually try to understand the model's performance by considering different combinations of I mean different combinations of values to the tuning parameter, or different machine learning models for the same data set. Okay, so if you this is a good summarization of everything. Now let's suppose if you are training a if you're training a model, and then you have you have three different machine learning models, and you want to choose which machine learning model best fits your you know y- your data set. Okay, your criteria, you want to find out, you have many classification methods available. Out of many classification methods that are available, you have to pick the best classification method that suits your data set. Okay, now I have taken three different classification methods. Let's suppose this is 1, 2, and 3, or different machine learning models. So for every machine learning model, I am I'm actually training and testing every machine learning model with different combinations of the data set. So now what I'm doing here is that I have taken the first 75% of the data as testing set, and last 25% of I mean, this is training data set and this is test data set. Now I have fed this data. I mean, I use this data to train this particular model. And then I have, once the model is trained, I use this test data set to test this particular model. And the result that I have got is, out of 6 test points that I do have, I have got 5 correct results and 1 incorrect result. Okay. So that is the performance when we train the model using this data set and test the model, and these are the results when we test that particular model with this test data set. Okay, so this is the first result that we have got. Now the second step that I'm doing here is that break the data set in such a way, in this particular way, such that this would be our training data set and the rest would be our, I mean, this is our test data set and the rest would be our training data set. Now again, we train the same model with this with this training data set, and then once the model is trained with this data set, we are going to test the model again with this data set. Once we test with this breakup, we got these results. We got 4 correct results and 2 incorrect results. And again, we have done the split in this way. Okay, so now this is the fourth block is our testing data set. 1, 2, 3 is our training data set. Here, third block is our testing dataset. 1, 2, and 4 are training datasets. Now, if you look at this, 2 is our testing dataset, 1, 3, and 4 are training dataset. Again, train the same model with this training data, which is 134, and then test the same model and test the trained model with this test data set. Okay, so then now what's happening is that uh, now let's calculate this particular result. Once we trained the model and tested the model with with this particular data set, we got this data as 1 and 5. Okay, so this is the test result. Correct, it has predicted one correct result and five incorrect results. And now again, we have we are doing the last combination, which is we are considering the first data set as test data set, 2, 3, 4 as training data set. Again, train this particular model using these 2, 3, 4 blocks as the training data set and predict the results using this first data set. And now you got the the accurate, I mean, the results on the test data set as 6 correct and 0 incorrect. So this is what cross validation actually do is cross validation will break up the data set into different combinations. So if you want to break this total data set into 4 parts, it has combined all possible combinations with this 4 parts, right? So it has picked fourth block as testing, third block as testing, second block as testing, first block as testing. So once it depends on. So now we are actually breaking the whole data set into four blocks, right? So we call this as fourfold cross validation. Okay. So depending on the number of blocks that we are dividing the given data set, the name of that particular cross validation is actually chosen. The whole concept is we have created or divided the data set into all possible combinations using the 4 blocks, and then we rigorously trained, we continuously, I mean, we one after the other we have trained this model and tested the model using different blocks, I mean different blocks of the data combinations. And then we have got the test results of every model that we have trained with different combinations of the training data. And now what you will do is you will accumulate all the results here. How many number of correct results that we have got? 5 plus 4, which is 9, 10 and 16. So when we train the model using cross validation, I mean, when we trained and tested the model using this cross validation or combinations of different data blocks using fourfold cross validation, we got the correct results as 16. And what about incorrect? Incorrect is 1 plus 2, which is 3, 5, 8. So total we got 8 incorrect results. Now we have done with the model 1. Now go back to model 2 and do the same thing. Again, pick the 4 possible combinations of again we are going to do for the same way for the second model. Again, pick the total, I mean, pick the different combinations of the blocks. This is 1, 2, 3, 4. Now train this model. So now training the second model using this data set and testing using this data set. It got these results to me. I mean, it got some different result to me. Okay. And now again, when you get the, you know, when you are going to train the second model, I mean, train the model using the um, second combination of blocks. Okay, so you will get some different you train this and test this, you got some result. So similarly you will do with all this combinations and you will get these results. And again you will again train the third model with all the combinations. So you will get these results. Now once you have got these results, the summarization of different results based on different combinations of the data sets. Now you don't really need to bother whether you have to choose the last block as the testing data set or the first block as the testing data set or second block, third block. You don't need to bother about that. What you are doing in cross validation, you are taking every combination into consideration and you are repeatedly doing the training and testing with every combination and you're getting a summarized result. Once you got the summarized result, you can see that the accuracy of this is high, 18 correct results, whereas here it is 16, it is 10. So when you have to choose one model out of these three, you will choose this particular model. Okay, so that is what basically cross validation is do. It take all the possible combinations of the data set based on the um, number of blocks that you want to divide your data set. So if it is 4 blocks, we call that as fourfold cross validation. And now in the extreme case, if you call each sample as one block, okay, here we have divided the entire data set into 4 blocks. Let's suppose if you have 100 data points in this data set, so you are using 25 data points as your testing data set, 75 as your training data set. Okay, so that is what 4 block means. I mean, you are dividing that into 4 blocks. 100 by 4 would actually become 4. 100 by 4 actually becomes 25. So each block actually counts 25 points. Okay, and then now if you consider every single sample as a block, what actually happens is that you would call each sample as a block. This leaves, and this is called as leave one out cross validation. Okay. So when you consider every sample as a block, you call that as, and this is an extreme case. So what you're going to do, you train the model with every other data point, and you will use only one data point as your testing data set. So such kind of uh, breaking the data set is called as leave one out cross validation. And in practice, we divide the data set into 10 different blocks, and we call that as 10th fold cross validation. And you repeatedly do the same thing, train the model 10 different times with testing, with test data being 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's how you actually choose the test data, combine the total data set into different combinations and use that for testing. Okay, so that is what actually cross validation actually will do is. So simple example is, get the result for every um, combination of the data set, or every possible combination of dividing the data set into different blocks, and get the summarized result. And based on the summarized result for different models, choose one model. Or in the other case, you can also understand it this way. So not only choosing one model out of different models. So this cross validation can also be used to tune the parameters. Okay. So like we wanted to use a method that involved a tuning parameter. So in our KNN model, the tuning parameter is K. You want to come up with the best K value. Okay. A parameter that is not estimated, but just sort of guessed. For example, K nearest number has a tuning parameter. Then we use 10 cross validation to help find the best value for the tuning parameter. So now we use this cross validation, 10-fold cross validation, to choose the best value for the K. Now let's suppose we have chosen K is equal to 3. Okay. And then this is the data set that is given to us, and we have chosen K is equal to 3. And now we train the KNN model with K is equal to 3 with all possible combinations of this data set. So we train and test this using 10 different data sets. Okay. And then we got accuracy as 92%. And now when again do the same set of thing using K is equal to 5. Okay. When now do the same thing with K is equal to 5. And now then we got the accuracy as 83%. When K is equal to 7, we got the accuracy as 100%. When K is equal to 9, we got the accuracy as 83%. Okay. Now, when we got these different results, the summarized results, we choose the tuning parameter K value as 3 because that gave us 100% accuracy. So this is the way that we tune the parameters, or this is the way to choose one model out of different models available for any kind of machine learning stuff that we do. Okay, so this is called as cross validation. Even if you look at this, we have generated a graph. So we have taken different K values. If you just look at this graph, we have taken different K values, and we plotted a graph of accuracy for every K value, and you pick the K value where the accuracy is too high. So if you look at this particular point here, the accuracy is high, so you will come up with the K value of that particular parameter. So this is called as tuning. Okay, tuning is done using cross validation. So this is how important cross validation basically is. Cross validation, what to summarize cross validation? Cross validation will actually do combine all the possible combinations of data blocks. Data blocks can be fourfold, tenfold, or leave one out. Cross validation. So leave one out. Each sample, in extreme case, each sample can be one block of the data set. Okay. And then use every combination of that block to tune a parameter or to train a model or to choose a model. So here you train different models. Here you have trained the same model using different k values. So this is tuning. So the same KNN model but different k values. So your goal is to find the best k value where the accuracy is high. But here in this case, your goal is to choose the best model out of different models that are available that fits your data, and you are getting high accuracy. Okay. So that is how you choose a model or tune a parameter that your model is depending on. Okay, is that clear? Are you clear about cross validation? So this applies to every machine learning model or every stuff that we do in machine learning. So we do cross validation, tune the parameters, do the cross validation, choose the model which is best performing on it. Okay, you understand this?
Yeah.
Okay. So that is what cross validation is. Now you understand how do we tune the value of k? How do we get the value of k? So you do cross validation. And when I say cross validation, this has to come to your mind. Everything that we do so from now, tuning the parameters will be done through cross validation only. Okay. So now you do cross validation, get a value of k and use that value of k to train your model. So once the model is trained, it will actually go ahead and do its own predictions or on own classifications or whatever it is. Okay, so that is how you tune the value of k. So let's suppose now if you consider here, if you choose k is equal to 3 again, if you get accuracy as the same, you can take, if you take 3, k is equal to 3, you might get 92% accuracy, 5 83% accuracy, 7 100% accuracy. So you will go with k is equal to 7 and train your model or prepare your model for further classifications for the new data points that are given out. Okay. Now, this next thing, as I told you, we will just see how do we calculate the distance from one point to the other point. Okay. I have this particular data set given here, and I have plotted all this data set in this particular graph. Okay. 40 65. So 40 65. So PCT is this. Okay. At 65, we have 40. Okay. So 65, 40, this is the point. In such a way, I have plotted all the points in this particular graph. Now, this is the given point for us. And this point is nothing but 60, 42. Okay. So this point, which is given to us, is 60, 42. 60, 42 is nothing but these values. This is PCT value of that particular patient, and 42 is the CRP value of that particular patient. Okay. Now in our data set, we have two dimensions. If you look at this, we have two dimensions. One is CRP and the other one is PCT. Based on the CRP and PCT, we calculated, we plotted this graph, PCT on x-axis and CRP on the y-axis, and we plotted all the graphs. And we also have, based on the data set that is given, it is given that these points, the green points are bacterial points, and these orange points are viral points. Okay, virus points. So now our goal is that given k is equal to 5 and a point is given to us, this is, this is chosen parameter by the user. We have to actually tune that. But let's suppose for this example, we have tuned this value as k is equal to 5. Now what you have to do in KNN, you have to find out 5 nearest points to the given point. Okay, for that, what you have to do, you have to calculate the distance from every point and then you know sort the points in descending order and pick the top 5 values. So we have calculated the distances from this point to every other point and then sorted the distances in the increasing order. And now we have picked the first 5 points. Okay, because k is equal to 5. And out of the first 5 points, uh, 3 are bacterial. Look at this green color, they are bacterial. So these 3 points are bacterial, these 2 points are viral points. So these 2 are viral points. Now, in this particular case equal to 5 range, we have 3 as bacterial and 2 as, virus. So we predict this, we classify this particular point as bacterial because the count of bacterial points closest to the given point is more than the viral points. So we have to classify this point as bacterial point. Okay, now to calculate the distances from this point to a given point, how do we calculate? Using the Euclidean distance, 60, 42 is one of the point and 30, 30 is the other point. Okay, so what you just have to do, so given point is 60, 42, and one of the point in the data set, as you have to calculate the distance from this given point to every other point, you have to do the same set of calculations for every other point. So given point in the data set is 30, 30. So let's suppose 30, 30 is one of the point that is given. So how do you calculate the Euclidean distance? 60 minus 30 plus 42 minus 30 whole square, right? 60 minus 30 whole square plus 42 minus 30 whole square to the square root. So that gives you the distance, which is 32.3. Similarly, you calculate the distance to every other point. Okay, so this is computationally expensive, given even if you're given a single point. When you have million points, you have to calculate the distance from every other point to actually find out or classify the uh, you know the distance, I mean the to classify the given point to a specific class. So this method is computationally expensive because again, if you have billion points, for every given point you have to calculate the distance to every other point in your data set. Okay, so this is how KNN actually works, and that is how you calculate the uh, I mean we compute the class of a given data point. Now it all works well when you have a balanced data in your you know in your data set. So if you don't have a balanced data, if you have imbalanced data, how does this KNN works is something that you have to, is something that you have to understand. Okay, let's look at this. So problems with imbalanced data. When groups are of equal size, KNN is unbiased. Okay, it's not going to be biased. It actually go ahead and choose you know it works perfectly as we discussed. But when groups are imbalanced, like if one of the data points are more, like if we have like 1,000 data points belonging to one class and just like 6 data points belongs to virus, this will be biased, right? Because uh, we are just taking the count of the points here. So when the count is more, it becomes unbiased. Okay, let's suppose if I have taken uh, so if you look at this, so the distance that I have taken is just 5, but as the concentration of these points is more, every time it will actually I mean override these data points. So if you even take this particular circle, so even when we covered all the data points of virus, still their count would be less than this concentration, right? So in this is what biased, I mean imbalanced data set means. In this case, KNN will be biased. It will be more biased to the class where the data points are more. So how to overcome this? So to overcome this, one can use small k value. So when they use small k values like 2 or 3, what happens is it will just take 3 points. So it will negotiate the concentration. If you take more k values like k, if you take k is equal to 100, anyways, so the concentration would be more of these points. So as these points are just 5, every time when you always classify the given point as bacteria when you go beyond k is equal to 6. Okay, when you go beyond k is equal to 6, what happens? The concentration is always, the rest of all the data points are always bacteria only, so the count of them will anyways decrease even they stay far from the given point, right? So in that case, what happens? You always classify the data point as bacteria. So one way is to actually choose the smaller k values. When the k is small, which is less than this one, so it will be little unbiased. When k is going to be large, when k is equal to let's say 15, even if it is covered like this, say as these are just 6 points, 6 points, so the rest all points has to be bacteria. So even if they stay far away, we classify this point as Even if this given point is staying far away from these bacterial points, we still classify that as bacterial points. That is the problem with unbiased case. So what you have to do in this case is choose a smaller k value so that you can get rid of that imbalanced data condition. Or the other way is you can put more weight on groups with fewer data points when calculating the distance between the unknown observations and the data point. What is this basically weighted calculation means? I mean, the weight of each neighbor is commonly calculated using the inverse distance weighting. Okay, so when you calculate the distance weight of each data point as inverse to its distance, then what happens when the distance increased, weight is, I mean, the weight of the data point is increasing. When the distance is decreasing, weight and distance are inversely proportional, right? When the distance decreases, weight increases. When the distance increases, weight decreases. So just take the value of it. When distance is equal to 2, what is weight? Weight is equal to 0.5. When distance is equal to 5, weight is equal to 0.2, right? So when weight is increasing, distance is decreasing, the vice versa. So when distance is decreasing, weight is increasing. Okay, so they both are inversely proportional to each other. Now when we calculate these weights and using these weights to classify the models, what happens? It will give more weight to the points which are closest to it, right? So when a given point is more close to it, it give more weight to it, right? When the distance is coming to be so large, when the distance of these points are coming to be so large, so 1 by 100 becomes 0.0001. So the weight of that would be become very less. That's how you do the weighted calculation. So and using those weights to actually predict the label of that particular class. Okay, so that is how weighted calculation will actually help you to overcome this imbalanced condition. So let's suppose if you take a simple example of this, um, I'm just trying to explain you this. So now we are going to do the weighted calculation. So you can 1 by distance is the parameter that we are doing. So let's suppose this is a distance 2. Okay, this is a distance 2. This is a distance 1. And this is a distance 5. And this is a distance 6. And let's suppose we have 4 points at far distances. Okay, so 5, 6, 10, and 20. Okay, let's suppose we have 4 points and the larger distances. Let's suppose we have 4 points, 5, 10, 6, and 20. Sorry. Okay, and 20 is the one of the points. Now these are the distance that we do have, and once we take k is equal to 7, what happens? These four, let's suppose if these 4 points are coming down into the circle, so we classify them as bacteria, because 4 points in that circle are bacteria and 3 points in that circle are virus. So now if you don't take the weighted calculation based on the number of points, we assign that particular point to bacteria. But you know, this is an unbalanced condition, unbiased or imbalanced data, right? But if you calculate the weights, what happens? Calculate the weight of this particular green one, I mean virus one. Let's suppose calculate the weights of viruses. So 1 by 2, that becomes 0.5, and weight 2 becomes 1 by 2, right? So weight 2 becomes 1 by 2, which is 0.5, right? 1 by 2, that is 0.5, and weight 3 would become 1, right? 1 by 1 will become 1. 1 by 1 will become 1. So the total weight of this virus now is 2, right? 1 plus 0.5 plus 0.5. Now if you take the weights of the green points, what are the weights of green points? 1 by 10 will be 0.1, 1 by 20 will be 0.05, and 1 by 5 will be 0.2, 1 by 6 will be something around 0.2, something like 25, let's suppose. Okay, now even if you calculate the total weights, how much did become 0.6, right? So 2 is much greater than 0.6. Even though the number of points are 4 here, the weighted calculation became much lesser. So this is how we by using the weighted calculations, weighted distances, or um, uh, we actually we have successfully classified the point as virus. So the weighted distance became 2, but the count is just 3. So if you just take the counts in the imbalanced data set, you will do a wrong classification. But if you that can be overcome using the weighted distances. So this is how you calculate the weighted distances. Is this clear? This is how we handle the imbalanced data sets in using when you're trying to use the KNN method. Okay. So now what is the optimal value of K? K is recommended to be an odd number. Why K has to be odd number? If you are taking an even number, it may create an ambiguity, right? So if you're taking even numbers, what actually happens again, if let's suppose if a green point came here, so there in this case, there will be three oranges and three greens. You would not be able to actually classify to a specific class. But when you take odd number, again, it always has to be 3, 4 or 4, 3 or something. One will be more or less than the other one. So you always have to take an, it's recommended to take on an odd number to not get into an ambiguity conditions when you have equal number of data points belonging to different classes in the K value that you have chosen. Okay, value of K should never be equal to 1. So when value of K is equal to 1, what happens? It, let's suppose there is an outlier here. Okay. So all the virus data points are here, all the bacterial data points here, but there is an outlier which is residing inside this bacterial points. That is an outlier. But if you take, let's suppose if you're given with a data point, something close to this. So, and if you're choosing K is equal to 1, what you are doing, you will be assigning that to virus. But if you're given a new data point here, and if you want to classify this particular data point, and when you take K is equal to 1, and it falls under virus, right? Like it falls, I mean, as this is close to virus, when K is equal to 1, you assign that as virus. So when you choose K is equal to 1, it is more prone to outliers, right? So you should never choose K is equal to 1. The rule of thumb for choosing the K value is root of n. If the number of points is, the thumb value is root of n. If the number of points is 1000, it is always good to choose K as 100. Okay, and you can tune the values around this K to for calculating the better accuracy. But ideally, thumb rule is K value always has to be equal to root of n, and then you can tune for the best K value around these values. Okay, so now if you go back to this particular data set, how many data points that we have? We have 12. So root of 12 will become 2 root 3, somewhere around what is the value of it? uh, what is the value of root 3? 1.7 or something, right?
Yeah.
2, 3, 2 into root 3. So that is somewhere around
1.73.
3.46. So this is somewhere around 3.46. So that is equal to, like somewhere around close to 4. And you have to tune and then you have to start tuning the values around that particular thumb rule value, so that you will get the based on cross validation, and then choose the best value where your best value of K, where you're getting the higher accuracy. It varies from data set to data set, and it's your job to do this cross validation and then getting the right optimal value for that K for better performance. So that is all about KNN, which is K nearest neighbor, and that is how it classifies the um, data points into different data sets. Okay, now going back to the second method, which is naive Bayes classifier. So again, as I told you, every classifier goal is to classify the given point to one set of class. I mean, any of the classes in the any of the specific class given in the data set. Okay, so naive Bayes is one another approach of or one another classification method. Okay, um, so how does this actually work? KNN is just working using the distance calculation, right? It calculates the distance from every point and picks a K value, and then decides the value of class of a given data point. Now in naive Bayes, let's see how this actually works. Let's suppose we want to classify in whether a given email is a spam email or not a spam email. If you look at your Gmails, all the spam emails would automatically go to the spam folder. How Gmail is actually doing that? It is actually using some classification method to distinguish between the spam email and a not a spam email. Based on the result of that particular classifier, it will just move those items to spam folders. Okay, now let's see how naive Bayes actually. You already have studied about Bayes rule, right? We already studied about Bayes rule, posterior probability, prior probability, likelihood, um, and the generalization summation, right? We already have studied Bayes classifier, so I don't want to go back there, but let's understand how this actually works. So I just want to remind you one thing. When two events are independent of each other, then the joint probability will become just the multiplication of their individual probabilities. What is joint probability? P of A intersection B would become P of A into P of B when we consider A and B are independent, right? If A and B are not independent, then the Bayes rule would come into picture. What is the Bayes rule? A given B is equal to probability of B given A
Mm.
into P of A by summation of I is summation of every I, right? So this is like how to represent this? Summation of every combination of this P of A by B into P of P plus P of B by A into P of A. So this is what Bayes rule is. Okay. When they are dependent on each other, when they are not independent, this is the actual thing that you have to use. When they are dependent, when they are independent, the joint probability will become just the multiplication of the individual probabilities. And now, so you got this, right? So this is what we have studied in Bayes rule. Okay. Now, what naive Bayes, how does this naive Bayes actually work is that now given an email, you want to classify email is spam or not. So these are all like not spam emails and these are spam emails. Now, we have taken the words that frequently occur in, you know, in normal emails. Okay, so these are the frequent words that are happening in a normal email. So dear happens 7 times in the given data set. Okay, so you're given with a data set, and that data set has these words. Like you're given a data set with different messages, email messages, and inside that they are saying this is spam, this is spam, this is spam, this is not spam, this is not spam, and this is not spam. Based on this data set, you came up with this particular data set. So in non-spam emails, you got dear as dear. How many times this is? Um, 8 times. You got dear as 8 times. You got friend as 5 times. You got lunch 3 times. Money 1 time in this non-spam emails. In spam emails, you got dear only 2 times, friend 1 time. You haven't got lunch anymore. I mean, you don't see lunch in any of these messages that you have got, but you got money 4 times in the spam emails. Okay, you have to take all those words happening, unique words happening in this, uh, in the data set. Once you got these unique words, you're going to calculate the probabilities, okay, of those of those words. So give a probability of word dear in a normal message. Okay, how do you calculate that probability? You calculate that probability by taking this count by total count, right? So how many more words in dear? So in a normal message, so you won't consider, so you are restricting the data set or the points to only this space, item space. Okay, So the your space is getting constrained to this one because you're already saying given normal message, the probability of dear happening, the word dear happening. So how do you calculate the probability? What are the total number of words in normal messages? So it is 3, 6, 7, 8. 8 dears. And how many times this happened? This is 5, this is 3, and this is 1. Now, what is the total count here? 8, 16, 17, right? So out of 17 words, you got dear 8 times. So 8 by 17 will become 0.47. Okay. 8 divided by 17 will become 0.47. Similarly, calculate the probability of friend given a normal message will be 5 by 17. Okay. So dear would be 8 by 17. This would be 5 by 17. Lunch would be 3 by 17. And money would be 1 by 17. So this is all the probabilities that you have calculated given a normal message. Probability of dear given a normal message. And also you have calculated the probability of dear in spam emails. Probability of dear given a spam. So that would become, what are the counts here? 2104, right? So what is the total count here? 4, 5, 6, 7 is the total count. And then dear you're trying to calculate, that becomes 2 by 7. What does 2 by 7 will become? 0.285 or something. So you are marking that as 0.29. So friend will become 1 by 7, which is 0.14. 1 by 7 would be 0.14, right? And lunch would be 0.00. Money would be 0.57. Money is nothing but 4 by 7. So once you calculated these probabilities, okay, and then what you're doing, you're calculating the prior probabilities. Prior probability, what is the probability of a normal email? So that is 8 by, how many emails are there here? 3, 4, 5, 6, 8 emails are there here, right? So 1, 2, 3, 4, 5, 6, 7, 8, 8 normal emails and 4 spam emails. So probability of normal email is nothing but 8 by 8 plus 4. Probability of spam email is nothing but 4 by 4 plus 8. Okay. So these are the prior probabilities. Uh, and then these are the likelihoods that we have got. Now, if you look at the Bayes rule, okay, the denominators will be actually same. Okay, the denominators for calculating given a new message, given a new message considering a spam email, right? So this is a new message and we are trying to calculate the probability of spam given a message is nothing but, it's nothing but probability of message given spam into probability of spam by generalization term, right? Probability of message given spam into P of S plus probability of spam given message into P of M. Okay, we do that calculation, right? So denominator will be same for both of them for spam or no spam. Even if you calculate the probability of not spam given a message is equal to probability of message given normal message or not spam into probability of normal message by, in the denominator you are going to get the same thing, right? The summation of both of them. So the denominator of this and this will be same. Is that right or not?
Yes,
Hello.
same.
Yeah, as denominators will be same, you can ignore the denominators. You can just concentrate only on the numerators. Okay. In the numerators, as they both are independent, you are going to just multiply the probabilities of both of them. Okay. That actually means so message. If you're getting a new message as let's go back here. If you're getting a new message here, now what is that you want to now you have got all your calculations and you also have understood that you are just bothering about the numerator in the base rule, you will forget about the denominator. Now you are given it a new message and you want to classify that as spam or no spam. Now you're given with dear friend as the message. Now you want to classify dear friend as spam or not spam. So now what you will do is you got all these calculations from the data set that you have got. The probabilities of, I mean, these are all likelihoods, right? Um, um, and now you want to classify dear friend. Now what you want to find out? So the message given to you is probability of spam given a message. What is the message that is given? Dear friend. Okay, so that is what you have to calculate. Now what this turns out to be, probability of message given spam into probability of spam. The message here is dear and friend, right? So now in naive Bayes, the probability of dear friend, message is dear friend given spam, right? So we are breaking this down to, we are considering dear and friend as independent variables. That is what naive Bayes will actually consider. Naive Bayes will consider that for computational efficiency, it will just consider that events are independent of each other. So it is considering that dear and friend are independent words happening. They'll consider this as independent of each other. So that becomes probability of dear friend given spam will becomes, as dear and friend are independent, we can just write that as probability of dear given spam, probability of dear given spam multiplied by probability of friend given spam. So you are just converting this conditional probability to a multiplication, because you're considering the naive Bayes approach will basically consider dear and friend as independent of each other. Okay. So now, and the last term that is pending is P of S. That is how you calculate the probability of spam given a message. So once you calculate that probability for spam and probability of normal message given a message, you calculate the probability of this and this. Let's suppose if this is x and this is y. If x is greater than y, you classify this message as normal message. If y is greater than x, you classify this message as spam message or spam email. So that is how you naive Bayes will actually do the calculation. Okay. So what naive Bayes will do is it will calculate the probability of spam given a message, and probability of not a spam given a message, or probability of class 1 given a message and probability of class 2 given a message. And the other assumption that it makes is, it makes that every item is independent of each other. That is the assumption that it will make. So once it makes that assumption, so that becomes the joint probability will become just a multiplication of um, individual probabilities. Okay. So then we just multiply. So if you look at this dear friend now, you are going to calculate probability of normal message, which is 0.67. Probability of dear given a normal message, what is the value of that? It's 0.47. And then probability of friend given a normal message, that is 0.29. So you are going to calculate all of them and you got the probability as 0.09. So that is the probability of, proportional to probability of normal message probability of normal message given a message here is dear friend. Similarly, you are calculating the probability of spam given a message, which is dear friend. So that is nothing but probability of spam into probability of given dear given a spam and probability of friend given a spam. Okay. And now if you calculated all these probabilities, and then you have calculated the multiplication and you have got 0.01. So now what is happening? The probability of normal message, the probability of normal message given a particular message is 0.09 is greater than 0.01. So we classified this message as normal message, not a spam message, because the probability is less. So that is how naive Bayes will actually classify anything that is coming up. I'll also show you a numerical example on how does this actually work. But this is how naive Bayes will actually do the classification. It calculates the posterior probability by considering the events are independent. Okay. dear and friend are independent. That is why naive Bayes is called as naive, because it assumes that even though there is a relation between both of them, it assumes that they are independent. Even though considering them as independent, naive Bayes will actually perform well in doing the classifications. We will just go and see that. But now let's suppose you got another message which is lunch, money, 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 money. Okay. So this is the new message, new email that you have got. Now you want to classify this email as spam or not spam. By just looking at this message, you can say this is a spam email, right? It has money so many number of times. So that doesn't looks like a normal message. But now what naive Bayes will actually do here is what you have to understand. Now let's calculate the probability of this particular message. Probability of normal message into probability of lunch given a normal message into probability of money given a normal message is coming up 4 times, because 4 monies are there, right? Now if you calculate this probability of n, again the same calculation, right? Probability of n is 0.67. Probability of lunch given n is lunch given n is 0.18, and probability of money given n, which is 0.06, right? So you're doing that calculation and you got this particular value. Now if you're going to calculate the probability of this message being a spam, that becomes probability of spam, which is 0.33 multiplied by probability of lunch into s, which is 0. Look at this. So lunch into 0 is just 0. Money into s is 0.57 whole to the power of 4. As this is 0, this whole value is becoming 0. And then as 0 is less than 0.00002, we are classifying this message as normal message. And here is where we are doing a wrong thing. So it doesn't matter money comes 1,000 times or 2,000 times. When you have lunch in it, it will never consider that as, you know, um, as a spam email. Okay, because 0 multiplied by anything will become 0. So it will always consider the messages with lunch as normal messages. So it is not classifying well. The only reason why it is not classifying well is that you're having some value as 0, which is nullifying every other thing, right? 0 multiplied by anything will become 0. So in other words, if a message contains the word lunch, it will not be classified as spam, because 0 into anything will be 0. And probability of spam given a message will always goes to 0, right? And that means we will always classify the message with lunch in as normal, no matter how many times we see the money. Even if you are getting money for 1,000 times, you'll always consider that as spam email. Now to avoid this problem, what you have to do, you have to get rid of the 0 values. So what you have to do, for every word you automatically add 1, so that there is no chance that that will go to 0, right? Once you add these black boxes, okay, uh, add 1 count to each word every time. So even though you don't see that word in that particular emails, you will actually add 1 count to it to just avoid this particular case, okay, where the classification is not happening, right? So once you do that, once you add that, again if you do the probability calculations and all that stuff that you have done, now this becomes, what does this becomes now? Again, I'll just do a calculation for this one stuff for lunch. Earlier it is 0, because 0 by anything is 0. Now if you want to calculate this becomes 1 by, this becomes 3 now. So this becomes 3 now, this becomes 2, this becomes 1, and this becomes 5, right? So this will become 1 by 3 plus 2 plus 1 plus 5, right? So that becomes um, 10, 11. This is becoming 11. So how does this actually looks like? This is what the probability of lunch of spam. So initially we have 0 by 7. As we have added 1 count, 1 by 7 plus 4, because this 4 is coming up because we are adding 1 to every other feature, right? That's why we're getting 4. And in the numerator, this count is becoming 1. Okay. Earlier it is 7. Now it become plus 4, because you have 1 added for every feature. If you have 6 words, this becomes 6. If you have 8 words, it becomes 8. So this is nothing but 1 by, count of the words plus number of features. Okay. So that is how the new formula will become. Now none of the words will become zeros. And now if you calculate the probability of, I mean the posterior probability of the same message, for normal message we got the probability as 0.00001, and for spam we got it as 0.00122. Okay, and now you classify this as spam email. Okay, so that is how we avoided by adding just one to every word's frequency. We have avoided the problem of getting zero and misclassifications. So this is called as Laplace correction. Okay, in naive Bayes, this is called as Laplace correction. Laplace correction is nothing but 1 by what we do. Laplace correction is nothing but initial frequency, initial frequency plus 1 by total frequency of the words plus number of futures. Okay, so if you want to understand this better, initial frequency, if you in earlier, what is the probability of money? Money is calculated by 4 by 7, right? So if you go back to the old slide, how did we calculate it? 0.47. 0.47 is calculated by 4 by, this is 4, 5, 6, 7. 4 by 7, right? 4 by 7 would be 0.57. That is how you calculate it. Now with Laplace correction, how we are doing it? The Laplace correction, initial frequency is 4 by total frequency is 7. The total number of words in non-spam is 7. You are adding plus 1 to this plus number of features. That means 4. So this becomes 5 by 11. Now even if you calculate this, so this is the Laplace correction. So Laplace correction, what we are in the numerator, we are adding 1, and then denominator, we are adding the number of features. Okay. Even if the initial frequency is 0, that becomes 1. Okay, now if you just calculated using these blocks, here the count is 5 by what are the total count? 3 plus 2 plus 1 plus 5 will become 11. So that this is nothing but equal to this, and this is the Laplace correction that we are applying. This is exactly the Laplace correction. Adding 1 to the initial frequency by number of features to the total frequency of words in the given message. Okay, so this is how naive Bayes actually works with Laplace correction. So we no more going to get any zero more values. Every time we just add one count to everything, every other word or feature that we are actually trying to consider in your classification methodology. Okay, so that is called as Laplace classification. Naive Bayes is called naive because it assumes all features are independent. I have told you, right? Dear friend, it considers dear and friend as independent words or independent features, even though there is a correlation. So if you're trying to have, if your data set has blood pressure and like, uh, someone has high blood pressure might also have like high cholesterol. So if your data set has blood pressure and cholesterol, they're actually correlated with each other, right? So BP and cholesterol levels are strongly correlated. If BP is high, the cholesterol might also be high, right? But what naive Bayes will actually do is it will consider them as independent and calculates the individual probabilities of both of them, right? So they consider them as independent even if they are dependent of each other. So that is the naive thing in naive Bayes. Okay. However, naive Bayes discards these correlations and these treats each features as if they are independent of each other, independent of the others once the class is known. Okay. So that is the naive approach in the naive Bayes thing. Okay. So this is all about naive Bayes classifier. Okay. And now if you want to, the next approach that we're going to talk about is Gaussian naive Bayes. Okay, so Gaussian naive Bayes is always treats is will always deals with normal distributions. Even though if the data is not normally distributed, it considers that the data is normally distributed and performs this classification. Okay, so how does this naive Bayes actually work? Is like, so this is the given data set for the naive given data set. Now, if any new data set is given to you, you want to classify that as cancer or healthy. Okay. So now I have plotted all these data points on a particular graph, just this one-dimensional data set on a particular graph. And now for the healthy data set, I consider this data is normally distributed, and I have calculated the mean of this data set and standard deviation of this data set. Mean is nothing but sum of all the points by number of points. Standard deviation is nothing but square root of x minus me whole square by the 2 into. How do we calculate the standard deviation? How do we calculate the standard deviation, which is root of variance? How do we calculate variance?
1 by n
Mm,
x minus x bar whole square. Summation of x minus x bar whole square.
good. So that's how you calculate the standard deviation. And now what is the formula for normal distribution? This is the formula for normal distribution, right? This is not multivariate normal distribution. This is just normal distribution in um, of a one-dimensional data set. Okay. So 1 by root of 2 pi into sigma e to the power of minus x minus me whole square by the 2 into sigma square. Okay. So now when we calculate the mean and standard deviation of this data set, we have drawn the graph of that particular data set. So the mean is at 1.5. So the mean of this is at 1.5 and the standard deviation is 0.61. Okay. So the standard deviation is 0.61. We like this rule, right? 3 sigma rule, 2 sigma, 3 sigma, minus 2, minus sigma, minus 2 sigma, and minus 3 sigma. We know this rule. So that is standard deviation. Now, based on these values for the healthy candidates, we came up with this particular graph. And at a given point, if you want to calculate the probability density, you just have to submit those values here. What is the standard deviation that we have calculated? 1 by root of 2 pi, 0.61 square, right? Into, you are just substituting the point x is equal to 2 here and substituting the values of mu and sigma in these, and calculating, coming up with the value of f of x. Okay. So that is how you calculate the probability at this particular, probability density at a given point. So you calculate the probability of that particular point using this formula. That's how you calculate the probability at any given point. Okay. Now, for the second class, similarly, for the second class, which is cancer, I calculated the mean and standard deviation and I plotted this particular graph. Now I have plotted the graph, the Gaussian distribution for healthy and also the normal distribution for cancer, Gaussian or normal, whatever it is. Now, if you're given a new data point, okay, so now we plotted these graphs based on the given data set and by calculating the mean and standard deviation. Now, if you are given a new data point, now you want to classify whether this given point is cancer or healthy data point. Okay. So now if you are given this particular data point, what you do is you calculate the probability density of this point for healthy and also for the for cancer. So this is the probability density for cancer. This is the probability density for healthy. Okay. So now plug in the values for both of them. So what are the values for cancer? If you look at the cancer standard deviation, which is 2.8, and the standard deviation is 0.82, mean is 2.8, and substituting all the values, and the point that you have got here is 2.6. Okay. Oh, the point that you have got here is 2.6, right? The point that you have got here is 2.6. This is 2.6. So plug in these values. The x is given as 2.6 and you're trying to find out the probability density, the value of this for cancer, right? So you got that as 0.47. Similarly, you're trying to get the value on this particular curve, which is on this particular distribution. You're trying to find out the probability density of this given point. So substitute this in this particular function again. So for healthy, what is the standard deviation? For the healthy, standard deviation is 0.67, mean is 1.5. Substitute those values and the x is 0.67. So now you got the value 0.13, right? So now you got the probability density functions at these 2 points. Okay. The probability density or the probable, you can say, probability would be on a range, which is the area under the curve. But as it is a 1 point, you got this as the probability of the, what you got, probability of cancer given a message, right? No, this is probability. This is the reverse probability, right? What you're trying to calculate, your your space is constrained to cancer, or right in that cancer you're trying to find out the probability of this particular point, which is 2.5. Okay, so in this graph only, in this data set only, for this data set only, you're trying to calculate the probability. You're not considering this data set in this particular graph, right? So that becomes uh, prior probability. So you're given cancer, in that you're trying to find out the probability of this particular point. Okay, so now that's what you have calculated. You have calculated prior probability. But if you just look at this particular graph, this is the intersection of these two graphs, right? So anything that is before this will have the highest probability of healthy. Any point beyond this will have the highest probability for cancer. So the cutoff I can say is 2.17. Any PSA value less than 2.7 is healthy. Any PSA value less than greater than 2.17 is said to have cancer. Okay, that is what you can understand by drawing this normal distribution. So if you actually say this, I mean, based on this particular thing, if you want to classify these are the given messages, and these are what we have classified based on the assumptions that we have made. So 4.17 is less than 2.17. I mean, it's greater than 2.17. So that is cancer. 3.4 greater than 2.17, cancer. These are all cancers because they all these values are greater than 2.17. But 2.1 is less than 2.17. So we mark that as healthy. 1.6 is less healthy. 2.5 is greater than 1.7. We have cancer. So we have marked all of them as healthies. Yes, 2 is less than 2.17, 1.7 is less than 2.17, 0.58 is less than 2.17. We marked all of them as healthy data points. But if you look at this, these 3 points we classified wrongly. Okay, we classified them as healthy when they are cancer, healthy when they are cancer. So the accuracy of this would be, how many total points are there? 5, 8, 10, and 14. Out of 14, we have classified 11 correctly. So the accuracy of this is 11 by 14. Okay, so this is how it actually works. But there is, I mean, it's just multiplying by. Now what we want to get, given a point, probability of a particular class given a point, this is what we have to calculate, right? Again, this comes down to multiplying this with probability of that particular cancer. So that is what we finally do. It's just a calculation. So again, this is the Bayes rule. We are doing the posterior probabilities is nothing but probability of PSA, which is the dimension that we heard, are healthy. Given a PSA value, the probability of a PSA value given healthy by probability of healthy PSA by this one, probability of cancer into PSA by this one. So I mean, both the classes we are summating for the different classes. So these numerators are same and we can just ignore them. Okay, for different classes, we are just doing that and we can ignore them. So what we can only consider is we can just consider the numerators. And now we got the values of probability of PSA 2.6 given cancer, that is coming as 0.47, 0.13. We got these values and probabilities, and these are prior probabilities, right? So how many data points are cancer data points? 3, 6, 7 data points are cancer data points, and 7 data points are healthy data points. So the probability of cancer is 7 by 7 plus 7, which is 0.5. Okay, so now we got them as 0.5, 0.5, and finally we are calculating the posterior probabilities, which is 0.5 into 0.13. For healthy it is 0.5 into 0.13, and for cancer it is 0.5 into 0.47. And the probability of cancer is more than probability of healthy, so we classify that as cancer, the given point as cancer. Okay, so it looks, you cannot directly predict from these graphs because the density of the points could be different. If the cancer is just 3 points and the healthy is 8 points, if you don't multiply with this um, prior probabilities, you will not get the right result. So this is the final probabilities, the posterior probabilities. And you understood from this, right? So why we ignored the denominator. So even if you consider denominator, It won't change the result because these two are the same. Dividing by the same number will not affect the numerators. Okay. That's what I mean to say. Let's suppose if you are comparing 2 and 4, we know 2 is less than 4. But when we divide this by 2 on both sides, even if you get the same result, 1 is less than 2, the same result we will get. We are just scaling, so you can just ignore the denominators for better you know for time saving and to reduce the computational complexities. Okay, so that is how you actually do classification in naive Bayes. In naive Bayes, what we have done, we have calculated the mean and standard distribution of every class for the given dimension, which is PSA. This is the dimension PSA. For every class, we calculated the mean and standard deviation, and we plotted the graphs, and then pro- we got the prior probabilities using the probability density functions, and then you also have got the so these are likelihoods actually. We got the likelihoods from these formulas, and we then got posterior probabilities of cancer and of the different classes, and we have just multiplied them to get the posterior probabilities. We ignored the denominators. Okay, and now if I have one dimension here, right, we have just PSA. Now if I got two dimensions in any naive Bayes, what we are just trying to do, we are just trying to ignore the dependency or the correlation between the dimensions. We are just trying to consider them as independent variables. Okay, now again, what we're going to do, as I told you, they both are independent, so we treat every dimension as an individual attribute or individual dimension, and we just focus on only the dimension. We will not focus on you know the dependency or the correlation between two dimensions. So for PSA, we again calculated the mean and standard deviation, which would be the same as before, 2.8, 0.82. Look at this. So we considered everything as independent in naive Bayes. That is the naive thing in both Gaussian naive Bayes and also normal naive Bayes. Okay, so Gaussian is like an is for continuous variables, and when you are trying to predict a value for it or classify based on a continuous values, you go for Gaussian Bayes, and naive Bayes is just for discrete values. So you calculated again the standard deviation and mean for cancer class for PSA. Similarly, you will do for age as well. So this is for normal distributions for age. Is if you have third dimension, you will just construct the same things again and repeat the same things for everything. Probability of healthy, you will again 0.5. Probability of PSA by healthy, we have calculated this. Probability of PSA by healthy, we calculated here, right? 0.13. Where is that? This is what we have calculated. Similarly, you calculate the same thing for A's for healthy only. You follow the same approach, calculate for A's as an independent variable, multiply everything and compare and assign that to a particular data. If you have four dimensions, you will get another mean and standard deviation for for third dimension for class one, for third dimension class one, which is height. Let's suppose the third dimension is height. Calculate the mean and standard deviation for class 1 for the third dimension, and again calculate the likelihood of that particular third dimension and just multiply with this. As we are considering everything as independent, it would just falls to be multiplication. Okay, and then based on the values, based on the by comparing the outputs or the posterior probabilities, whichever is higher, we assign the point to that particular class. So this is what naive Bayes actually means. Is this is how we do the classification using naive Bayes. So you understood this naive Bayes, Gaussian naive Bayes, um, and KNN and cross validation. And I'll tell you why we don't actually do full Bayes. I mean, why don't we consider the dependency between the dimensions? Why we cannot actually do that, or why we can't achieve that computationally, is what I'm going to discuss that tomorrow. But this is before, I mean, this would be, you have to clear with this is what you do in the real world. That is just to understand why we cannot go with full naive Bayes and how that is computationally ineffective is what we will try to understand tomorrow. So the only naive thing in naive Bayes is that we consider every dimension as independent to each other. Even though there is a strong correlation between both of them, we consider them as independent. Like if you take the example, if PSA, if you take the same database, same thing, if PSA is BP and ACE is, let's say instead of ACE, you consider cholesterol, they are highly correlated with each other. But we consider them as independent and we do the when we try to do the classification. That is the naive thing. Even with that naive, even considering them as independent, naive Bayes will do good in most of the cases. Okay, that's the reason why we still learn it. And why we don't consider this dependency is what I'm going to discuss tomorrow by explaining you the computational, by comparing the computational efficiency between computational costs between naive and full Bayes theorems. Okay, full Bayes is nearly impossible to achieve. The computational cost is so high for it. That's the whole thing. I'll also explain you intuitively why that is costly and what happens inside that and all that stuff. Okay. Any questions so far?
No.
Okay.
No.
You understood them, right? The three cross-validation, Canon, naive Bayes, and Gaussian naive Bayes.
Yeah, that's
Okay. Now, this is the most important stuff in support. I mean, in classification, support vector machines, which is widely used, and this is very effective. Um, After support vector machines, we have something called as rule-based classifiers. With that, we will be done with classification. So I think today and tomorrow we will cover in support vectors. We have three different cases. I'll walk you through them shortly. And also I want to walk you through the computational efficiency between full Bayes and naive Bayes approaches, and why full Bayes is not at all achievable, and why we shouldn't consider that is something that we will close by tomorrow. And then in the next week, we will go with rule-based classifiers and evaluation of different classification methodologies. Like we have done this accuracy calculation is the only thing that we are depending right now, right? So similarly, we have something called as F1 score, precision, recall. So these are all the parameters that are used to evaluate the machine learning. Machine learning method or machine learning model performance. Those are the evaluation parameters to ROC, AUC or something. I mean, we will talk about machine learning models performance metrics. With that, we will be done with classification, and then we will start with clustering. Clustering means it's an unsupervised learning. We already talked about supervised, unsupervised, and reinforcement learning, right? So clustering is an unsupervised learning. We will not give labels to the data. It automatically tries to find out the patterns in the data, right? So what about this naive Bayes and Gaussian naive Bayes? Is this supervised or unsupervised?
supervised.
Why?
Because they are classifying the data into given features.
Yeah, so we are passing the labels. We are saying that these points are belonging to cancer. So we are giving the label and we are giving the answer already. So if these PSA levels are there, these patients are cancer patients. If these PSA levels are there, we are trying to say these are healthy patients. We are giving the label, and we are also, if a new data point is given, we are just trying to predict that label only. Okay, when the labels are given, and that's a supervised learning, and we call that as so this naive Bayes, KNN, wherever you give labels in your data or use labels to feed or train your model, those all falls under supervised learning. Okay, just take a break for 5 minutes, and then we will start support vector machines. This is very important in the whole classification learning stuff. Okay. So now, as we have completed decision trees, Canaan, Naive Bayes, and Gaussian Naive Bayes. So we are going to study about support vector machines now, which is one of the widely used and famous classification method. Um, so so let's understand the math behind support vectors machines first, and then we can go ahead and understand what support vector machines actually is. Okay. So if you look at this particular line, we traditionally know this notation of representing a straight line y is equal to mx plus b, right, where m is the slope and b is the intercept form of it. So you can represent this line using this particular format. Let's suppose if you want to calculate the slope, intercept of this is 1 and slope of this is somewhere something, what is the slope of it? So if you take this particular point, 4 comma 3 is one of the points and 2 comma 2 is one of the points. And if you want to calculate the slope, y2 minus y1 by x2 minus x1, which is 1 by 2 is the slope. So if you want to represent this line, so this becomes 1 by 2 into x plus 1 is the intercept, right? Um, so this is how you represent this particular line. But so if you take this particular line, you will not be able to represent this line in this particular format, y is equal to mx plus c, because the slope of this line is infinity and this is parallel to y-axis. So this will be represented in traditional way. This will be represented as x is equal to 3.5 or something. So this is not matching to this particular format, right? So in machine learning, this format of representing a straight line will not work. So what actually works is the general notation of a straight of a line is ax plus by plus c. So this is the general notation of a straight line of a line. So going forward, we will not use this notation anymore, y is equal to mx plus c for a straight line. The notation that we use is ax plus by plus c is equal to 0. So this is the actual notation of representing a straight line in two-dimensional space. So we can convert this to this format, which is y is equal to mx plus c format, right? So what you just have to do, you just have to do some math. Move this ax and c to the other side and divide, and just divide this with b and b. You will get this format, which is matching y is equal to mx plus b, right? So now onwards, even if you cannot represent this particular line in this format, but this can be represented in this format. Here b will become 0, a equal to 1 and c is equal to minus 4. So now any line can be represented in this format. Okay. Right. So that is the first thing that you have to understand. Now we are moving from y is equal to mx plus c notation to another notation of the straight line, which is ax plus by plus c is equal to 0 notation. Okay. So that is what we are moving forward to, and that's what we have to, that is the takeaway from this particular slide. Now let's understand how the straight lines will vary by changing the values of a, b, and c. Okay, that is all what excuse me. Excuse me. That is all what we are trying to understand here now. So what is going to change? So if you take this line, if you converted this line to this particular format, what we will try to understand in the next few slides is, yeah, you might be aware of this stuff, but I just want to revise. So how the straight line will vary when we change the value of a, and how does the violence vary when we change the value of p and change the value of c? How the line will move around this 2D space is what we are going to understand. So we change the value of a and see how the line is moving, and we change the value of p and change the value of c, and how the line is moving is what we will understand. So okay, so we are going to change the value of a, change the value of c, and change the value of p, and see what how the line is actually moving. And now if you take the first case, so this line is represented by this equation, and if we convert that to y equal to mx plus c format, this is what we get. Okay, so this is the slope of the line and this is the intercept of the line, right? So the intercept is 1, 4 by 4 is 1. The slope of this line is 1 by 2, which is 0.5. So that is the slope of this line. Now We changed the value of a from -2 to -1, and the rest all remain the same. What happened? The line just got rotated around the intercept point. Okay, so this is the intercept, which is this part, right? Now the line just got rotated. That means the slope got decreased from 1 by 2 to 1 by 4, from 0.5 to 0.25. So slope got decreased. Okay, and if we change this to -2 to -4, the slope became 1, right? 4 by 4 became 1, and the line has become moved this towards this part. But if you look at this, everything, all the line is rotating around the intercept. Every line is joining at intercept, right? So slope is increasing, the line moves this way. If the slope is decreasing, the line is moving in this direction, right? If the slope is decreasing, it's moving in this direction. The slope is increasing, it is moving in this direction. So when we change the values of a, it is rotating on the intercept. Intercept is nothing but this value, which is 4 by 4, which is 1. So when you change the value of a, this the line is changing on the intercept form, right? The line is just rotating around with intercept fixed. Now let's see what happens if we change the intercept itself. If we change the value of c, okay, here we change the value of a and see that it is rotating. And now we change the value of c, what is happening? So if initially this is 4, right? If the value of c is -4, it is like this. And if we change the value of -4 to -8, what it has become, it moved little up. Now the intercept became 2. The slope remains the same. When the slope is same for these two lines, they're called as parallel lines. So the new line will be parallel to this, but the only thing that got changed is it moved up as the intercept is like increasing, the value is increasing, it moved up. And when we make 4 to 0, it moved down. So when we change the value of c, what it is happening, it is moving up and moving down parallel to this direction. So when you change a, it is rotating around the intercept point. When you change c, it is just moving and up and down. It's moving up and down parallel to this particular line, right? So what happens when we change b? Okay, what happens if we change b? The value of this is changed now, which we have seen how the line is behaving when we change a, and we have seen how the line is behaving when we change c. Now let's see how the line is behaving when we change the value of b. Initially, when the value of b is 4, it's something like this. When the line is when the value of b is increased to 8, so it is rotating, and the intercept is also changed. The intercept changed, the slope changed, but they are just merging at this point. The reason why it is it's rotating around this point is, like, let's see, if we change the value to 2, what's happening? When we increase that value, it is coming down. When we decrease the value of 2, it is going up. That means um, when we increase this value, what happens? Intercept will decrease and also slope will decrease. Slope is decreasing, intercept will also move down. The line is moving down. And when we decrease this value, slope will increase and also intercept will move up. Okay, but they're all coming down to merging at point -2, because that is where x value is equal to 0. So when this part is 0, whatever that you make here, that will be the same, right? When you make x is equal to, sorry, when you make y is equal to 0, so here what you are doing, you are making y is equal to 0. So when you make y is equal to 0, whatever change that you do in the numerator will go back and converges to 0. So that always will stay same. So that's the reason they all the points are moving at merging at 0. So what you have to understand is, by changing the values of a, b, c, we are moving the line around. We are moving this particular line, right? By changing the values of a, b, and c, we are moving this line around. So in support vector machines, the main agenda is to find out a line which separates the points effectively. Okay, we are trying to find out a line that separates these points effectively. So what you have to do, you have to find out an optimal line. So this is one of the line that separates these data points, and you can draw in another line, right? So this is one line, this is another line that separates this point, this is another line, this is another line. So out of all these lines, what is the best line that separates this data effectively is what you have to understand, right? So for that, what you have to do to find out that optimal line, you should be able to move this particular line in different directions, right? You should be able to move this line here and here, and see how well that is actually giving us the classification results. So that is what support vector machines, actually support vector classification, will actually try to do. It tries to move that particular line so that you will get an optimal separation. Okay, how we are changing this, how we are moving this line, by changing the values of a, b, and c. When we change the values of a, b, and c, you are moving that line here and there. So what you have to find out, you have to find out the optimal values for this a, b, and c, so that you will get an optimal line for the classification. So that is all it comes down to. So that when you change the values of a, b, and c, the line is moving. So you need to move the line to different positions and find out the optimal line that separates the points effectively, right? So that is the whole point. By let's just look at this. If you change this the points now, if you change these points, if you change the values of a and b, the line will just rotate, and you will find out the this is how the line rotates, right? When you change the values of a, b, and c, this is how the line rotates. And now, yeah, you have to find out an optimal line that separates the points effectively. Okay, so I just want to go through a simple thing. Now let's just look at this. What is called as an optimal line? If you consider this particular diagram, so to separate these 2 points, we came up with the two lines. This is one of the lines that is classifying, that is effectively separating these 2 points, and also this is another line which is effectively separating these 2 points. Okay, so this is line 1 and this is line 2. Okay, this is one line 1 and this is line 2. So these two are effectively separating the training data set. These are training data sets, right? So this is training data sets. So both these lines separated the training data set effectively. But when you get a test point, so when you get a test point, okay, so this is the test point that you have got. So this test point is above this particular line, so this is classified as yellow point. So it makes sense because this is far from this point, but it is close to this green point. But this line, when it is classifying the test point, it is classifying this point as yellow because it is on the other side of this line. It means to say it is towards yellow line, but this point is more closer to green points when compared to yellow points. So this line is not effectively doing the classification. So this is not an optimal line. This is an optimal line, right? This is the best line that is separating the data and also performing well on the testing data set as well. Okay, so that is how you change the values of A and C and find an optimal line. So optimal line will be decided by the values of A, B, and C. Okay, so that is what actually finding out an optimal value means. And as I told you, uh, if you calculate the points above this line and see what it is happening, the line is minus 2x plus 4y minus 4. That is this particular line, minus 2x minus. Now take any point above this line and substitute in this equation. What happens? Minus 2 into 5, right, plus 4 into 4 minus 4. What is this value coming down to? Minus 10 plus 16 minus 4. Okay, so that is minus plus 2, right? You got, for this you got this as plus 2. And take any other point, take this point which is 2 comma 3. Okay, you're taking this value as 2 comma 3. For 2 comma 3, substitute the same thing. What does this become? Minus 2 into 2 plus 4 into 3 minus 4. So what does this will become? Minus 4 plus 12 minus 4. So this becomes 4. Okay, so this is plus 4. And now take any point below this line. Okay, let's take this point which is 5 comma 2 and substitute in the same equation. So this becomes minus, what does this becomes? If you substitute this in this equation, you will get something like this, right? So what is that? Minus 2 into 5, which is minus 10, plus 4 into 2 is 8, minus 4. So that comes down to 14, minus 14 plus 8, uh, which is minus 6. So for this point, you got the value as minus 6. And take any other point. Take this point, which is 3 comma 2. Okay. And substitute the same thing. For 3 comma 2, what you're getting? Minus 6 plus 8 minus 4. Okay. What you are getting now? Minus 2. So for this, you got minus 2. Okay. Let's just observe, for every point above this line, you're getting the positive values, right? And for every point below this line, you're getting negative values. Okay. When you substitute that point in this equation, you're getting the negative values. Okay. So if I represent this equation as h of x, I can say h of x is greater than 0 for the points above this line, and h of x is less than 0 for points below this line. You got that? Hello?
Yeah.
Yeah. Now, if you take point on this line, let's suppose if I take this particular point, which is on the line, the point is 4 comma 3. And if you substitute that inside this equation, what you will get is something that is interesting. Now, you understood that every point that is above that line is getting a positive value, and for every point that is below this
Yes.
line is getting a negative value. Now, if you take any point that is on the line and calculate the value of that particular function, or the equation, what you will get is, let's suppose take this point, which
Zero.
is, you got it as 0, right? So you got 4 comma 3 as the point, and if you substitute this in that equation, you get minus 4 into 2 8 plus 4 into 3 12 minus 4. So you're getting that as 0, right? So if you take any other point, if you take this point which is 2 comma 2 and substitute in this, that becomes 2 comma 2 is the point that you're trying to find out, and if you substitute that value, we got minus 4 plus 8 minus 4, so getting 0. So any point on this line has values equal to 0. H of x is 0 on this line. So to simplify this, what we have got this, any point above this line has h of x greater than 0. Any point below this line has h of x less than 0. Any point on this line has h of x is equal to 0. Okay, this is another finding. All right. So that is one thing. So you're clear with this, right? So you find out an optimal line, and you found out that any point above that line has h of x greater than or equal to 0, greater than 0. Any point less below that line has h of x less than 0. Any point on that line has h of x is equal to 0. Right? So that is the second observation. So by changing the values of A, B, and C, we are able to rotate the line in that space so that you can find out an optimal line that separates the point effectively. And once you find out an optimal point, you find out that all the points above that line has h of x less than greater than 0, and all the points below that line has h of x less than 0, and all the points on that line has h of x is equal to 0. Okay, so that is another finding. Now, this is also interesting. So if you actually see this, you got this line as h of x is equal to h of x minus 4 by minus 4 is equal to 0, right? That is first line. Now, I am going to find out a line parallel to this line, where the distance between them is equal to 1. Okay. Okay. So now I'm trying to find out a new line parallel to this line and has a different intercept. Okay. So if you take this particular line, this is the middle line, right? Minus 2x plus 4y minus 4 is the middle line. Minus 2x plus 4y minus 4 is the middle line. And now what I'm going to do is I'm going to try to find out a line parallel to this particular line, so that on the right hand side it is equal to 1. Okay, so that is this dotted line is this line. So they both have same slopes, so they will be, parallel. All the three lines will be parallel because all of them has equal a and b, right? What is the only thing that is changing? The intercept is only changing, right? The intercept is only changing. When we change the value of b, what will change? It will just move up and down, right? Right or not? So here, what you are just changing, you are just changing the c value, right? You're just changing the c value. When you change the c value, what will do? It will just move up and down, such that you just make sure the distance between them is 1. Understood? Can we represent that way? So this is the middle line. As we changed only the value of C, the line just moves parallel to it, but some distance above to it. It just move parallel to it. When it just move parallel to down towards it. When here we are decreasing the intercept. Here we are increasing the intercept. Let me represent these lines in y equal to mx plus c format, so you'll understand it effectively. So if I convert this to y equal to mx plus c, what happens? Y is equal to minus 2x plus 2x by 4 plus 4 by 4, right? That is how you represent this line. So this becomes y is equal to 2x by 4 plus 5 by 4. So this is this line. If I represent this line, y is equal to 2x plus by 4 plus 3 by 4, right? So here intercept is equal to, slope of all the lines is same, so all of them will be parallel. Here intercept is equal to 1, here intercept is greater than 1, here intercept is less than 1, right? Less than 1. So as the intercept is less than 1, this line will move down. As the intercept is greater than 1, this line will move up. So now we are trying to find out a margin, right? Margin in the sense you are trying to find out two parallel lines above and below to it. Now what happens? Just look at now, all these three lines are represented by these three equations, right? This is this equation, this is this equation, this is this equation. Okay. So what we have tried here is we have kept the LHS the same, but the RHS is +1 and -1 for the above and below one, so that you got a line parallel to that, to the above and to the below. Any questions here, or is this clear? We're just trying to normalize. We're just trying to find out a line above to that, such that the left hand side, right hand side is equal to 1 and -1. Okay, so that these lines will become, if you look at this, the slope is not changing for these three lines, only the intercept is changing. 5 by 4 means, what is the value of 5 by 4? 4 by 4 is 1. That's the reason it is just connecting to the origin at 1. 4 by 5 is more than 1.2, right? 5 by 4 is nothing but somewhere around 5 by 4 is
1.25.
1.25. So
1.25.
it is just above this 1.25. So intercept is 1.25. So here x is equal to 0. So it touches the line at 5 by 4. That is what intercept is. Here x is equal to 0. Here x is equal to 0. 3 by 4 is 0.75. So it touches the line 0.75. As the slope are same, both the lines will be parallel to each other. So that is how we got two lines where LHS of all the three lines is same, but the right hand side is 1, 0 and 1 -1. Now let's see what happens. If we multiply this with a factor less than 1, okay, if we multiply everything with the factor less than 1, less than 1 in the sense 1 by 2 is one of the factors. What happens? The intercepts will increase, right? The slopes will remain the same. The slopes will always remain the same. Let's suppose if I multiply all these equations with 1 by 2, what happens? So this becomes minus 2x plus 4y minus 4 is equal to 2, right? And if you represent this, this becomes y is equal to 2x plus by 4 plus 6 by 4. So now what is happening? The slope is remaining the same. We increased this value much greater than 5 by 4. Initially it is 5 by 4, now it becomes 6 by 4. So this value is 1.25, right? 1.25. So this value will become, what is this value will become? 6 by 4, which is 3 by 2, 1.5, right? So this is greater than this one. So this will move little up. As we increase this factor, when as we make this much and much less, than if we make this 1 by 4, this becomes 8 by 4, which becomes 2. If we make this, if we multiply this with 1 by 6, this becomes 6 by 4. I mean, this becomes 12 by 4, right? If it is 1 by 4, it becomes 8 by 4. This goes on this side. Where is this? So this goes this side 4, 4 plus 4, 8, 8 by 4, right? So if you multiply this equation with 1 by 4, this line will go much further away because the intercept is increasing and this line will go parallel to this but much farther to this. Okay. Now if you multiply these equations with a value less than 1, I mean with value greater than 1. So initially we multiplied with 1 by 2. Now if I multiply this with 2, what happens? 2 minus 2x plus 4y minus 4 is equal to 1. So this becomes divided so that the intercept will keep on decreasing, right? When we multiply with a factor less than 1, the intercept will increase so that the lines will move far away from this particular line. And if you multiply this with a factor less than 1, I mean greater than 1, what this intercept will become? Intercept will decrease and they will some way go close to that optimal line. Okay. At some time, they will all go to that optimal line. If you look at this, as we keep on increasing the value of if you keep on multiplying the values, so the intercept will keep on decreasing and they will merge with this line at at some point. Okay, so this is how we find out some parallel lines at distance 1, at some distance, so that when we change that value, when we multiply that value with some factors, the lines are moving away from that and moving down from moving close to that line. So the whole point that you want to understand here is by just multiplying with some factor, what is happening is when we multiply these with some factors with factor less than 1, what is happening? The lines are moving, the parallel lines around it are moving away from it. Okay, the lines are moving away further away from it when we multiply this with factors less than 1. When we multiply with these factors greater than 1, the lines are coming close to this middle line, right? That is what it is happening. So we have found out few things with the max that we have understood. By changing the values of A, B, and C, we were able to rotate the points. We are able to rotate the line around the 2D space. So that is the first observation that we have done. And the second observation that we have done is, what is the second thing that we have studied? So all the points above that particular line has positive values, and all the points below that line has negative values, and all the points on the line has values equal to 0. And the third finding that we have got is by multiplying the line with some factors, we are able to move the parallel lines to the main line away from it, and we are able to move those lines towards that line, right? By just multiplying with some factor k, we are able to manage moving these lines away and towards this optimal line, right? So these are the two things, and how we are actually achieving that, we understood everything. And now we already understood this. Okay, now coming back, now we are slowly moving towards understanding the support vectors. So we understood the math behind it, and we also understood between these two lines, this is effectively classifying, this is not effectively classifying, even though they are separating the training data set effectively. Okay, now let's name these lines. The optimal line I was saying is called as the hyperplane. Okay, why we call that as hyperplane, I'll also let you know. Right now, as we are in a 2D space, we can call this as a line. Okay, and why we call them as hyperplane, I'll explain you to that shortly. Just make sure, wait for it. So now what I'm trying to do is, now we have a data set given to us. Okay, now what I'm trying to do is I'm trying to draw two parallel lines intercepting the two closest data points in the hyperplane. So initially what I'm trying to do is I'm trying to find out the two closest points in the two classes and trying to draw two parallel lines intercepting those two parallel lines. Okay. So those points which are close to each other, through which we are drawing the parallel lines, are called as support vectors. Okay, so these 2 points are called as support vectors in machine learning. Support vectors are nothing but the two closest points in the data set that is given to us, and through those 2 points we draw the parallel lines. Okay, that is, so those 2 points are called as support vectors. Any points, in fact, um, um, lying on this line, let's, if you have another point on this is also called a support vector. If you have another point here, that is also called as a support vectors. Okay, so these are the terminologies that you come through when you're trying to understand the support vector machines. Okay, so but we have gone through some understanding of the math behind support vector machines, but let's dive into understanding how does the support vector machines actually classify the data points or assign the class to a given data point. Okay, we'll just try to understand this now, right? So now let's understand, this is the 1D data set that is given to you. Okay, now you are given this particular data set where all the red dots belongs to one particular class and all the green dots belongs to another class. Now you want to find out an line that effectively separates these two data points. Now if you take this specific line, well, let's suppose this is the margin that is separate. I mean, this is the line, or this is the point that is separating these two points effectively. Now, if you take this particular point, this is the test point, and as this is towards, or this is towards the left side of this particular line, and we classify this as red line. Okay, and we if we get the test point here, as this point is towards the right of this particular line, we classify that as green dot. Okay, so this is classified correctly, this is classified correctly. But what happens if we get a test point here? So as this point is to the right of this line, we classify this as green point, but this point is close to red point, so this is a misclassification. What does that actually says? So we classified this as green, but this is technically close to dead red point, so this has to be a red, this has to be classified as red. But this boundary that we have taken is not effectively working in classifying the test points. Okay, even though it is working good in differentiating the training data set, but it is not working fine in the on the test data set. Now what do you think is the best line? The best line that separates the these two sets is take the edge points, the data sets, and find out a point which is middle to both of them, and place that interface or the separating line at that particular point. That would actually do a good separation, right? So that is what we are doing here. Focus on the edge of each cluster. So only focus on the edge of the points in both the clusters and use the midpoint between them as a threshold. Okay, so using the midpoint between them as a threshold, that actually classifies the data. Now, even if you get a point here, you're getting a right. This is rightly classified, right? As this is towards the red point, and it makes sense. It is close to the red dots, and classifying that as a red. That is good. And when you get any point towards the right side, you're classifying that as a green. Okay. So the best optimal line is finding out the edge of the clusters and making and taking the midpoint between them and marking them as a threshold is a good practice, so that the chances of misclassifying would be less. Okay, now you need to understand a few terminologies here. Okay, the one is margin. The distance between the observations and the threshold are the same and both reflect the margin. Okay, so from this threshold to this particular point, the distance is same as from this threshold to this red point, because we are trying to find out the midpoint between the points that are edge of this cluster, right? So the distance from this to this would be same as this to this, because we are trying to find out the midpoint. So these are called as margins. Okay, the shortest between the distance between the observation and the threshold is called as the margin. So this distance is called as margin. Now you have found you found out what are support vectors. Support vectors are these points, right? That the closest points in the clusters are called as support vectors. Okay, we just studied over here. These are the support vectors. What are support vectors? Support vectors are nothing but two closest data points, right? Two closest data points in the cluster are support vectors. So these two are support vectors, and this is the hyperplane, because this is in middle of these two things. Okay, so if you draw two parallel lines here, okay, so these two parallel lines are these two parallel lines. Okay, these two parallel lines in 1D case are these two parallel lines, and the middle of that two lines is called as hyperplane. Okay, so the line which is middle of these two lines is called as hyperplane. Okay, so we call this distance as margin. We call these points as support vectors. So these support vectors are helped us to find out the optimal hyperplane. Okay, right. That is the margin, right? When the threshold is halfway between the two observations, the margin is as large as it can be. Okay. So when the margin will be larger, when this is in between both of them, right? Then only the margin will be larger. If this is here, this is less and this is more. If this is moving towards here, this is less and this is more. So that is not doing the right classification. We already have seen when we move this threshold towards this red dots, the margin here is decreasing and here it is increasing, but it is not doing the classification rightly. What margin or what threshold is doing the right classification? When we place that in middle of both the points. Okay, when we when we keep this threshold between these 2 points, that means that is the case where we get the maximum margin. Such kind of classifiers where we are trying to do the where we are trying to maximize the margin are called as maximal margin classifiers. Okay, so you are trying to maximize the margin here. What is the margin? Margin is the distance from the support vector to the hyperplane. What is the hyperplane? Hyperplane is the plane which goes through the midpoint of the support vectors, right? That is called as the hyperplane. The distance from the hyperplane to the support vector is called as margin. So we are here. What you are trying to do, you are trying to maximize the margin, because margin maximization is giving you the right classification. So such kind of classifiers are called as maximum margin classifiers. Okay. So these are the different words that you have to understand before you go to any derivation, right? Now consider this case. Now what we are trying to do, we are trying to find out the edge points in both the classes, right? We are trying to find out the edge of each cluster, right? You're trying to find out the edge of each cluster and then you're trying to find out the midpoint between them. Now, if you consider this case, this is an outlier. Okay, and if you consider the edge of these 2 points, you are considering an outlier, and then you're taking this as a margin. And if you even if you get a test point here, so even if you get a test point here, you consider that as red, because even though that is close to green, uh, you're classifying this test point as red because it is towards the other side of the threshold line, and the threshold line got impacted by the outlier. So what we can say, maximum margin classifiers are super sensitive to outliers. So this is the outlier that completely changed the threshold actually has to fall somewhere here, which is looking exactly in between most of the green dots and red dots. But because of the outlier, the margin got completely changed. So you can say maximum marginal classifiers are more sensitive to outliers, or you can say super sensitive to outliers in the training data, and that makes them pretty lame. So this is completely a wrong approach. So now what is the solution for this? The solution for this is you should allow some misclassifications. Okay, so you should allow some misclassification. So when you allow misclassification, the distance between the observations and the threshold is called as soft margin. Okay, so here what you have done, this is an outlier, so this is impacting your accuracy. How do you know this is impacting your accuracy? So you use cross-fold again, like cross validation. A only solution to know anything is cross validation. So you train your data with these data sets and with the maximum marginal classifier, and you found the accuracy is very low. You will get the accuracy of around 20% or something. Okay, so then you will know that there is something which is impacting, so that you should start allowing misclassifications means you will not consider this point anymore. Okay, you will not consider this point anymore. Ignore this point and find out the other point which is closer to this particular point. So now you completely ignore this point and consider these 2 points as support vectors. the edges of the clusters, and then find out the midpoint between both of them. Okay. And now again do the cross validation and find out, and you will find out that accuracy of this increased to 85%. And then you you say just ignore this point and keep going with this with this particular margin instead of this particular margin. Okay. So when you allow misclassification, the margin, the distance from the threshold to the point will become is called as soft margin. When you don't allow misclassification, we call that as hard margin. Such kind of classifiers are called as hard margin classifiers. And when you allow misclassifications, when you're finding the margin, such classifiers are called as soft margin classifiers. Okay. SVM is a soft margin classifier. It allows misclassifications. And now the other question is, what is the best, how many points we should allow for misclassification? Okay. How many points you have to allow? Right. Just few more slides here, a few more diagrams that you have to understand. So once you allowed misclassification, when you get a test point, you are classifying that as green and it is close to green, so it's a good classification. That's the reason when you allowed misclassification, you got an accuracy, high accuracy. Okay. Now what is the best threshold? Okay. What is the best threshold? This is the best margin, or this is the best margin. How many misclassifications will actually how many misclassifications you have to allow is what you have to decide, right? Again, how do you decide? You decide that using cross validation. So how do you know which soft margin is better? This margin is better, this margin is better. How many misclassifications that you have to allow? You have to get an answer for that, right? How many? So let's suppose you allowed misclassification of this point, but still if you get the accuracy of 20%, what do you have to do? You have to allow much more misclassifications. So you come up with this margin and find out the accuracy, come up with this margin, find out the accuracy. You have to find out the best margin that gives you the more accuracy, right? How do you find out that? You find out that using cross validation. Okay, choose this margin and find out the results using cross validation or accuracy using cross validation. And let's suppose you got some value and increase the margin. If you're getting the accuracy more, you keep on increasing that and find out an optimal value that you want to achieve. So the answer is simple. We use cross validation to determine how many misclassifications and observations to allow inside the soft margin to get the best classification. So you do cross validation and then decide how many misclassifications is giving you high accuracy. Yeah, again, as I told you, when you do soft margins and allow misclassifications, those are called as soft margin classifiers or support vector classifiers. The name support vector classifiers comes from the fact that the observations on the edges and within the soft margin are called as support vectors. Okay. So the soft margin classifiers are called as support vector classifiers because anything that falls within the support vectors are called as support vectors. The name support vector comes from the fact that the observations on the edge and within the soft margin. So this is the soft margin now, right? So all the points within the soft margin are called as support vectors. Okay. So that is the reason why the name of the support vectors came into picture. Now let's just look at how the hyperplane looks like and how the support vectors and hyperplane looks like in different dimensions. If it is two-dimensional space, this is how it looks like. This is the hyperplane. These are the support vectors. These are the support vectors, and we allowed misclassification of this point for better accuracy, and we decided that using cross validation. So that now what happens? This is the hyperplane. This distance is the margin, this distance is the margin, this distance is the margin, and these are the support vectors, and this is also support vector as this is within the soft margin. Okay. So this is how it looks like in a 1D case. In 3D case, the hyperplane would be in this is the hyperplane, right? This is not a line. When we grow on increasing the dimensions, we call that as an hyperplane. The line in two-dimensional space, um, plane in three-dimensional space will become hyperplane in higher dimensions. Okay. So again, this is an plane that is separating the points in a 3D space. Let's suppose if you consider this as a room, if you consider this as a room, something like this room here. So this is your room and this is your floor. I mean, this is your ceiling. This is your ceiling and this is your floor. So some points are residing here, some points are residing below this. So now if you insert a plane here, or if you keep some cardboard here vertically in the room, the points above that will become will fall under one class, and the points will below that will be for one class. So this is the plane that is actually differentiating the points in a 3D space. Okay, so that is called as plane. So line in 2D will become plane in 3D and will become hyperplane in higher dimensions. Okay, so this is how we actually do classification in support vector machines. Support vector machines, all it will do is it will try to find out the support vectors. Support vectors means the edge of the clusters. Okay, the edge of the clusters will become the support vectors, and you will find out the line middle, which is in middle of both of those points, and we call that as an hyperplane. Okay, we call that as an hyperplane. So find out two edges and find out the midpoint of them will become a hyperplane. But if there is an outlier that is affecting the accuracy, we allow that to be misclassified and we ignore that point and go to the other point. And we call this as soft margin. Soft margin is nothing but this distance is called a soft margin. Soft margin is nothing but is the cases where we allow misclassification and finding out the margin. We call that as soft margins. Such kind of classifiers are called as soft margin classifiers. So all the points within the soft margin are called as support vectors. Support vector machines is a soft margin classifier. Okay, we understood what is a margin, what is a support vector, uh, what are support vectors, what is maximum margin classifier, hard margin classifier, soft margin classifier, soft margin, misclassification and cross validation and all that stuff in support vector machines. Okay, so this is the intuition behind understanding the support vector machines. And now I'll close this with some maths explanation. So now you know this, right? So now you know representing a line in 2D space as ax plus by plus c is equal to 0, right? So you represented this line as ax plus by plus c is equal to 0. This is the representation of a line in two-dimensional space. Okay, in three-dimensional space, how do you represent this? This is represented as ax plus by plus cz plus d is equal to 0. That is how you represent in 3D. How about 4D? You cannot keep on going with a b c something like that. You will run out of alphabets. So the general notation is w1 x1 plus w2 x2 plus w3 x3 plus so on plus wn xn plus d is equal to 0. Okay, or you can also keep this as b is equal to 0, any alphabet, that is fine. So you don't really need to bother about higher dimensions. So this x subscript will keep on going. So this is the general formula of a hyperplane. What is an hyperplane? In 2D it's a line that is separating the data points. In 3D it is a plane, right? A 2D plane that is separating the points, right? If you keep a plate in between, if you keep a cardboard in middle of the room, and the area above that plane is one part and the area below that plane is one half, right? Similarly, in 2D, if you consider this a line, everything that is above this line is one half, and everything below this line is one half, right? This is one half and this is one half. Similarly, if you have a room and if you have a cardboard inserted in middle of the room, everything above that line, above that will become one half. This will become one half and this will become one half. So the hyperplane will actually divide the area into two halves, right? Okay, so the general notation of the hyperplane is represented this as in this format. So the hyperplane in 2D is called as line, in 3D it is called as line. When it goes to higher dimensions, we call it as an hyperplane. And is there a simple way to represent this? In I'll call the hyperplane starting from now as h of x. Okay, and h of x can be written as w1 x1 plus w2 x2 plus w3 x3 plus so on wn xn, depending on the dimensions. If it is an n-dimensional hyperplane, it stops at wn xn plus b is equal to 0. The simple form of representing this is w transpose x plus b is equal to 0. Okay, so this is an simplest form of representing an hyperplane. What is W? W is nothing but W1, W2, W3, so on W1. What is X? X is nothing but X1, X2, X3, so on Xn. Now what we are trying to do, we are getting a transpose of this that becomes W1, W2, W3, so on Wn multiplied by x, that becomes x1, x2, so on xn. So this is 1 by n and this is n by 1. So the final one would be 1 by 1. What is this 1 by 1? w1 into x1, w1 into x1, w1 x1 plus w2 into x2 plus so on wn xn. So that is what W transpose into X means, plus B would again give you this equation. So the better representation of the hyperplane is W transpose X plus B. Okay, so from on now onwards, the representation of hyperplane for us is W transpose plus X plus B. W transpose are nothing but this A, B, and C, right? So now what you can say is, you know that A, B, and C decides the orientation of the hyperplane, right? Orientation of the line. Agreed. So A, B, and C decided the orientation of the line. Now, what decides the orientation of line here? This weight vector W1, W2, W3 will decide the orientation of the hyperplane along with the B. What does B represent? C. C will represent the intercept. The line, this B decides how far the line will move from away from that hyperplane. Okay. So technically, all these points will decide the rotation of that hyperplane. Here, in the generalized notation, W and B um, will decide the rotation of the hyperplane that separates the data points effectively. Now, what is our goal? Our goal is to, in 2D case, our goal is to find out the optimal values for A, B, and C. What is our goal now? The goal now is to find out the optimal values for W and B, weight vector and the B. So once you find out these values effectively, so you will be able to find out an hyperplane that separates the data effectively, okay, in higher dimensions. So this is an intuition behind a hyperplane. So now going forward, what you have to understand is that uh, hyperplane will be denoted by W transpose into X plus P. Okay. So hyperplane is denoted by equation which is h of x is equal to W transpose into X plus B. Okay. Now h of x is equal to W transpose X plus B. Okay. Now, if you have this hyperplane, which is h of x, and this is denoted by W transpose X plus B, right? Right. So now every point above this line has h of x greater than or equal to 0. Every point below this has h of x less than or equal to 0. Every point on this line has h of x is equal to 0. That is what we have seen, right? That is one of the notations. So every point above this line has h of x greater than 0. Every point below this line has h of x less than 0, right? So let's suppose if you want to uh, highlight them, like these are one of the points, like these are one set of data points, I mean one set of class, and on the other side you will have the other different class points, right? That is what all this is about. This hyperplane is actually trying to find out the separation between these two different classes. Okay, right. So now let's understand this. Now, given a vector, given a 2D space, now given two data sets, okay, two different data sets. One is the circles. You are given with two different data sets. Right? You're given with two different data sets. One is these points, and the other one is some kind of some other data points. Okay, you are given with some other data points on the other side. So on the other side, you got these data points. On the other side, you got these data points. Okay. You got these data points on the other side. Now, the goal is what is SVM's goal? What is the what is that SVM is trying to do? SVM is trying to do the closest points in both the clusters, right? It is trying to find out the closest points between both the clusters, and it is trying to find out the middle point of both of them. Now, the closest clusters in this is the closest, these two are the closest point, right? So you will try to find out a line that is intercepting the closest points, and the line which is going through the middle of both those lines is called as hyperplane. So this is the hyperplane. So this is support vector, and this is the support vector, as these two lines decided this hyperplane. So in support vector missions, what we do is we find out this is hard margin classifier, because we are not allowing any misclassification at this point to just understand a separable case. So here the data is linearly separable, right? So you can separate this data linearly. So you don't need to bother about soft margin for now. This is a linearly separable case. We are able to separate this data linearly with a linear hyperplane. Okay. So now we got this vector, right? We got the hyperplane, which is h of x. Okay. So now we got this hyperplane, which is h of x. Now h of x is equal to 0 is this particular line. So this is important. Let's understand. So these are the parallel lines that intercepted the support vectors. Okay. When we represent this as h of x is equal to 0, we are trying to find out a parallel line where h of x is equal to 1 and h of x is equal to minus 1. So this lines, the intercepting lines, then that intercepted support vectors are now represented with h of x is equal to 1 and h of x is equal to minus 1. We scale h of x in such a way that we get this line as h of x is equal to 1 and h of x is equal to minus 1. That is what we have seen in this case, right? So we got a line, we optimized this line such that the line that is going to the support vector should be able to represented by h of x is equal to 1, and the line which is going through the support vector of other line is represented by minus 1. Okay, we optimized the values in such a way. Okay, so now I am going to represent this line as h of x is equal to 1 and h of x is equal to minus 1. Now let's represent both of them as w transpose into x plus p is equal to 0, and this line is represented by w transpose x plus b is equal to 1, and the below line is represented by w transpose x plus p is equal to minus 1. Okay, so that is what it actually means. Now we found out these lines parallel to this hyperplane such that the right hand side is equal to 1. We just scale them, optimize them, that's all. It's just mathematical multiplication that we do. And now once we got them, now if you want to find out the distance between these two support vectors, what is the distance between both of them? Okay, now you want to find out the distance between these two support vectors. Okay, now before going to there, I also want, I mean, these are the representation of these lines, right? So this is this line which is going to the support vector of the other class is h of x is equal to 1, h of x is equal to minus 1. So these are the line representations of these two things. Okay, and now the other thing that you want to understand is, let's suppose I have this line. Okay, h of x. I have this line h of x. Okay, I have 2 points on this line. This is x1. Let me call this as x1 and let me call this as x2. Okay, now I can, when I substitute this point into this particular function, h of x is given by w transpose x plus b is equal to 0. That is this hyperplane, right? And now if I substitute h of x1 inside this point x1 inside this becomes w transpose x1 plus b is equal to 0. And if I replace x2 with this, h of x2 is equal to w transpose x2 plus b is equal to 0. Now if I subtract both of these, this becomes w transpose into x1 minus x2 is equal to 0. Okay, b and b will cancel. So I'm just subtracting this. Now what this says, w transpose dot product with x1 minus x2 multiplication of this is equal to 0 means they both are orthogonal to each other. W1, this vector, x1 minus x2 vector is this, right? X1 minus x2 vector is this. And this is nothing but h of x, which is going in the direction of h of x. And now it says W is perpendicular to this. That is what dot product of these two things is equal to 0 means. So this is a dot product, right, between two vectors. So dot product of these two vectors is 0 means they both are orthogonal to each other. That means W is orthogonal to x1 minus x2. x1 minus x2 is nothing but h of x. It's in the direction of h of x. So you can conclude that h of x is orthogonal to W, or W is orthogonal to h of x. Orthogonal to W, or W is orthogonal to h of x. Okay, so you need to understand that simple logic. So you're coming up with few derivations. So now going forward, we are representing hyperplane with w transpose into x plus b. You also understood how we actually came up with this equation. And now once we got the support vectors, we are representing the lines intercepting the support vectors as h of x is equal to 1, h of x is equal to -1, and the hyperplane is represented by h of x is equal to 0. And now we also understood that to find out this optimal hyperplane, we have to get the optimal values for w and b. How do we get the optimal values and all that stuff? We'll learn later. But we also understood that this vector w is orthogonal to h of x, and this is the proof for that. Okay, and the next thing that we are going to learn now is, so this is all basic mathematics to understand the support vectors. Once you are clear with this, you will be able to understand everything little easier. And the second derivation that I'm trying to prove right now is, what is the distance um, uh, from the origin to the hyperplane? Okay, so I'll say it this way. Like, let's suppose I'll come back with the same thing. Okay, now I have this hyperplane h of x. I have this hyperplane h of x, and now I want to find out the distance of this point from this hyperplane. So there is a point here. I want to find out this distance from this hyperplane. Okay, let's call this distance as xr, and this point is called as x, and this is the projection of this point. Okay, and this is the projection of this point. Now this is in this direction. We also have the vector w, right? As this is a projection, this will be perpendicular to this line, and the vector perpendicular to this h of x is w. So w vector will also be in this direction. So r is the distance from this line to this particular point, and this is the vector b. I mean, this is xp vector, and this is this vector x. So now this vector x is equal to xp plus r, vector summation. So xp plus r is equal to x vector, right? Summation of these two vectors will become this vector. And now x is equal to xp plus r can be represented as w by modulus of w, because we are just multiplying to give the direction for this r. Xp is a vector, r is a vector, x is a vector, xp is a vector. But r is not a vector. R is a scalar. That is the distance from this projected point to this actual point. To give this the direction of this r is nothing but the direction of w. So if you take the unit vector of w, so r will get a direction. So r's direction is same as w's direction. So that's the reason we converted everything to vectors now. So x is a vector, it has direction and magnitude. Xp is also a vector, it has direction. R also has now a direction which is same as the direction of w. Now you know h of x is equal to w transpose x plus b, right? Now if you replace this x is equal to xp plus r into w by modulus of w, right? I'll replace this in x now. So w transpose into xp. Replace x with this particular whole xp plus r into w by mod w plus b. Okay, so if you simplify this becomes w transpose xp plus r into w transpose into w by modulus of w plus b. Okay, now if you look at this w transpose, I can write all of this as w transpose xp plus b plus r into w is nothing but w transpose whole square, that modulus of w whole square. It's just a multiplication. So this cancels and this becomes r into w. Now h of x can be represented as, this is x, right? This whole part is x, can be represented as h of xp, right? If you look at this w transpose xp plus p, this is nothing but h of xp. Just in place of x, we got xp. So h of xp plus r into modulus of w. Okay. So now xp is a point on the hyperplane, right? This xp is a projected point of x on the hyperplane. So any point on the hyperplane will be equal to 0. So this goes to 0. H of x on the hyperplane is equal to 0. So xp is a point on the hyperplane. So this goes to 0. Now h of x will become r into modulus of w. So now r becomes h of x by w. Right? What is the value of r now? r is nothing but h of x by w. Okay, so this is the equation of distance of any point from the hyperplane. Okay, so this is interesting. So what is r? R is nothing but substitute the value of that point in h of x equation and divide that with the weight vector, you will get the distance. Okay, so now you got the distance of a point from, you came up with two conclusions. W is perpendicular to h of x. W is perpendicular to h of x, and the distance of the line from a given point from the hyperplane to any point is h of x by w. Okay, so these two are interesting things. Okay, now the next thing that you have to understand is that what is the distance of this hyperplane from the horizon? Okay, what is the distance of hyperplane from the horizon? Okay, you know the distance from any point can be calculated by this, right? So now using the same formula, h of x can be written as w transpose x plus p by modulus of w, right? This is a formula of it. Now we are trying to find out the distance of the hyperplane from the horizon. So x becomes 0, right? X is a vector now, which is a two-dimensional, that becomes 0, comma 0. So any weight vector multiplied by x will become 0. So distance from the horizon will becomes b by modulus of w. This is the distance of the point from horizon. Okay, from horizon is, this is the point. Understood? So x is equal to 0. So the distance from origin we are trying to calculate. So x becomes 0. 0, comma 0 is the point x. So this becomes 0. And now the remaining thing is b by w. So the distance of a hyperplane from the origin is b by modulus of w. Fantastic. So you calculated lots of stuff now. Now the last thing that we are going to close with for today is finding out the distance between these two vectors, these two lines. So how is support vector missions coming up to this hyperplane? it is coming up to that hyperplane from this, yeah, line. So now what the support you have gone through so much maths. Now let's bring out something that that support vector machines are trying to do. What the support vector machines are trying to do is they're trying to maximize the margin, right? They're trying to in a linearly separable case. Let's suppose what is linearly separable case is that a linearly separable case is now let's go one by one. Let's talk about linearly separable case. I'm saying about linearly separable. That means we are able to separate the data linearly. Okay, the first case that we are talking about is linearly separable case. That means you have the data that where you can linearly separate the data points using a hyperplane. So that means you have points something like this. Okay, you have points something like this. Like if you have crosses here, something like this, and you have we are just talking about linearly separable case now. We are not talking about any other. I mean, non-linearly separables or soft margins. We are just trying to talk about linearly separable case for now. Let's concentrate only on the linearly separable cases, and we can come back to the other stuff later. So these are the data points that we do have. Let's suppose make them a little farther away. Okay. So these are the data points that we do have. And this is a linearly separable case. We could easily find out a line that is separating both the points easily, right? So you have a line that is separating both the points easily. So you don't have any mixed match here. I mean, the points are not matching and not mixing, and we don't have strong outliers or something like that. Okay. So this is the case now we will start with to understand the different cases of machine learning. I mean, different cases of support vectors basically too. What support vectors are trying to do is find out the points, support vectors, find out the edges of the clusters, right? That is what it is trying to do. That is all what it is trying to actually do. And now let's construct the optimization optimization of this support vector machines theoretically, and then we can come back to the formulas and all that stuff later. So what the support vector machines are trying to do is trying to find out the support vectors, okay, and it's trying to find out a hyperplane which is in middle of both of them. Okay, so what this support, I mean, what the support vector machines are trying to do is it is trying to increase this margin, right? So the hyperplane is not here. The hyperplane is not here. When that hyperplane is near to that, the classifications is not coming to the coming correctly, right? So if you draw the support vector here, if you draw the hyperplane here, we have seen these cases. If you are drawing the hyperplane close to this point of the cluster, we are not getting the right classification. If it is also close to this, we are not getting the classification. So it has to be middle of the edges of the clusters. Then only we are getting the right classification, right? What support vector machines are trying to do, it is trying to maximize the margin. So when it is maximize the margin, it is getting the right classification, right? So when it is close to this cluster, it is this is minimum margin, right? The margin is minimum, but we are not getting the right classification in the on the test data set. So what it is actually trying to do, it is trying to find out the maximum margin. This is a linearly separable case, and it is trying to find out the hyperplane which is in between these two edges of the cluster. That means it is trying to maximize this margin. If the margin is here, the margin is here, it is called as minimum margin. The distance from the edge of the cluster to the point to the hyperplane is called as margin, right? So that is not giving the right results. What is that giving the right results? When we do maximize the margin from the edges of the clusters. Where it becomes maximum, when it exactly stays in between both the points, then only the margin will be maximum. If it moves this side, the margin will decrease. If it moves on this side, the margin will decrease. When it is exactly at the center, the margin will increase. So now our objective of SVM is to maximize. Objective of SVM is to maximize the clusters, maximize the margin. Okay. The objective of SVM is maximize the margin. Maximize the margin. What is the margin? Margin is nothing but the distance from the hyperplane to the edge of the cluster. So that is what it is trying to maximize. And so this is the objective of the SVM. So this is mathematically how we are going to achieve is something that we will see. When you say maximizing the margin, what is the margin? Margin is nothing but this distance, right? It is trying to maximize this. Now we have to come up with a mathematical formula for this and then solve the optimization for problem for that to find out the values. So now to represent this margin mathematically, we have to come up with a mathematical equation. How do we calculate the distance between two parallel lines? This is one parallel line and this is one parallel line. Distance between two parallel lines is nothing but how do we calculate the distance between two parallel lines? This is how we calculate the distance between two parallel lines. So that is what we have to actually maximize, right? So twice of the margin or whatever it is, that doesn't really matter, even if it is once. So let me show you how do we actually go ahead and do that. So now you know the optimization problem for SVM is to maximize the margin. That is the optimization problem. Now, how do we calculate the distance between, how do we calculate the margin or how do we represent that margin mathematically is what you have to understand now. Okay. So, okay. So can I say this? So this is the 2D plane, like this is the 2D plane. Now we came up with something called as data points, right? So we say this is a hyperplane and this is represented by h of x is equal to 0. And all the points above this hyperplane has h of x greater than 0. And all the points below this has h of x less than 0. This is class 1. Okay. This is class 2. And this hyperplane is actually trying to separate these classes. Now, to keep all these equations generalized, I am introducing a new variable called as yi. Okay, so this is yi. Yi for class 1 is +1 and yi for class 2 is -1. So my +1 denotes class 1 and -1 denotes class 2. And if I want to combine everything, I can write it as y of phi into h of x is always greater than or equal to 0. Okay, so if you consider this case, yi is +1 here, h of x is positive, so both will be greater than 0. In this case, you understood right? Here, y of I into h of x, I'm saying as greater than 0. What is y of I? Y of I is +1. H of x is always greater than 0. So both of the multiplication of this will be greater than 0. And for the denominator, h of x is less than 0. But yi is also -1. So -1 multiplied with something less than 0 will becomes positive. So that's the reason for combining all these points and generalizing them into a single equation will become y of I into h of x is always greater than or equal to 0. Right? So this is the generalized equation for all these data points. So I'm just introducing a new variable, which is y of I. Y of I into h of x is always greater than or equal to 0. So now if I transform h of x into the original form, ya into w transpose x plus b is always greater than or equal to 0. Okay. Now, this is the single equation representing the whole two partitions that this plane has created. ya into w transpose x plus b, whereas ya is positive for the class 1, ya is negative for the class 2. Okay, so that is the other thing that I would like to specify. Now the objective of SVM is to maximize the margin. Now we want to represent this margin. What is the margin? Margin is nothing but the distance from the hyperplane to the edge of the support, to the support vector, or the line intercepting the support vector. So now this is what we have to find out. This margin is what we have to find out. The margin is represented by this symbol, what we call stri or something, whatever it is. This is represented by the margin. Now we have to come up with an equation for this particular one. Okay, I'll show you coming the equation, deriving the equation for this margin and the optimization, and then coming up with the optimization for that is in the next lecture. Okay, I think that's all for today.